Alessandro Del Vecchio has the floor. Thank you, everyone. Thank you, Alessandro.
Thank you, Regan. Hi, everybody. So I guess today we don't have lunch. So today we'll talk about EMG motor physiology and what we have been, what we have been seeing in healthy individuals and in people with pathologies, specifically in people with neural lesions. So the outline, first we give you a perspective of what I believe there is. I think there is a lot of unexplored potential in the surface EMG. I think we can do more. Then we will look at the neural control of movement, where I will compare the upper and the lower limb. And the last part, I will give you a perspective on the EMG, if we can see it almost as a cure. I think in some application, it can almost seen as a cure. And you will see this later about what I mean. So just very briefly, I guess you all know about it. So you have in the spinal cord, in the ventral horn, some alpha motor neurons. This is the last pathway of movement. In this case, there are two motor neurons, and these innervate a specific number of muscle fiber, and this unique connection is called the motor unit. We don't have many of these cells, in the order of hundreds. If you think compared to motor cortex, like for example, just in the area of motor cortex projecting to the hand, we have billions of neurons that projected to innervate all the muscles. So the dimension that we have in the spinal cord is small, yet this dimension enables all the movement, a lot of movement that we can perform. And if we look, so one thing that I think we haven't been able yet to really identify from the surface EMG is this. So if we look at the physiology, the primary determinant of force is the motor unit innervation number, which means how many motor unit a motor neuron innervates. So the more muscle fiber you have, the stronger is the motor unit and the stronger is the total force. And for example, this is for the first dorsal interosseous muscle. There are around 120 motor units. So a relatively small number, and this is the innervation number, so the muscle fiber innervated by that motor unit, and these are arranged from the smallest to the biggest. You can see that there is a big proportion of motor units that have a very low innervation number, and 50%, because just a very small proportion innervates a lot of muscle fiber. I don't want to go into physiology here because we can discuss a lot, but this has many functional benefits to have this control scheme, especially for the hand. You can have a very dexterous control, yet be powerful at the same time. However, when we try to estimate this with the EMG, we don't find that. Yeah? So we usually find linear relations, as you will see later. So this is a central point that I would like to mention. So why we don't find this, and what is the reason that we don't find such physiological information? And I think the reason is that our methods are already very powerful, but yet not that powerful. But we can get there. This is the central part of this talk. So before we go there, let's look at the EMG. So you know a lot, thanks to Professor Ferrante, Professor Farina, we know really a lot now about how much what the EMG is. Yeah? So we know that you have, this is a simplified model, that you have like a cortical neuron that projects to several motor neurons, but you can also have an afferent neurons or an interneurons that generate some volleys. These volleys travel to the axon, then they innervate some muscle fiber. This muscle fiber twitch, generate an action potential, and we know that the EMG is the algebraic summation of all these action potentials, plus some noise. We know this because of, I think this is the pioneering study that showed that. So these some David Halliger stimulated the filaments here individually, and then you can see here the currents that was injected in 4 filaments. In this case that you see here, this was the EMG that was recorded when the currents was injected at all fibers, at all the filaments, all the axon filament. But they were able also to stimulate each one of these individually, and you can see the train of action potential of one specific unit. Then if you take these and you sum them, you can basically get the same signal. Yeah? So the EMG is the sum of the motor unit action potential. This is a physiological confirmation, but we have it as well from a mathematical perspective. because we can do the same if we decompose the EMG. Decomposition is the inverse of this. So basically you can identify this, and then you can go to this and compare to that. So you don't stimulate fibers, but you decompose them with the decomposition tools, and then you can reconstruct the EMG. So something that made me quite interested was to look at this plot. And this was a spinal cord injury subject. So if you know spinal cord injury, motor complete spinal cord injury causes severe damage of the spinal cord. And you only have a few fibers that are projecting to the muscle. And these few fibers generate an EMG signal that if you have experience with intramuscular EMG, it looks exactly the same as an intramuscular EMG signal, yet we are recording from the surface. And this is because it's a model, a selective model, like the Halliger that stimulated only few fibers. So you can basically, this is an EMG signal from a person with spinal cord injury, you can see that the decomposition, and when you look at the residual, so when you reconstruct the EMG, you can almost perfectly reconstruct the EMG. And you have a very low residual, whilst in a healthy subject, this is how usually the EMG looks like when you decompose it, you have a large number of residual. This is very, very big. You can see here, for example, this is a spinal cord injury EMG that is reconstructed after decomposition, and this is somebody that is healthy. And you can see that the root mean square error of the residual is dramatically different between the control and spinal cord injury. So in spinal cord injury, we identify almost all the signal. So the amplitude of the reconstructed EMG is similar to the baseline level of the noise of the EMG. Okay? So this tells us that the surface EMG, when there are few motor units, is extremely powerful. And why it is extremely powerful is because of that. So this a few years ago, we ran some studies where we looked at several muscles, and by using the technique I was telling you before, so by decomposing one muscle, you can look at the action potential, how it propagates to the other muscle. Even if some muscle, for example, this is the first dorsal interosseous, this is the tenor, or the vasti muscle, or the triceps, you can find a motor unit action potential in another muscle that comes from the muscle we were recording. So there is a lot of crosstalk. If you look especially at the monopolar, all the motor units that are in the FDI, you can find them if you record the tenor muscles. And similarly, this is from tenor to FDI, VL to VM, and VM to VL. So the monopolar signal is rich of information if you think about it. So it's far away from the target muscle, yet, so this is seen as a problem. But I don't believe it's a problem, this is a luxury that we have. Because we are saying here, with a surface electrode recorded in monopolar derivation, we can extract a lot. Why it is a lot? If you plot the motor unit action potential against the cross motor unit action potential, even size is preserved. So the motor unit in the FDI that are bigger, higher threshold motor units, preserve the size when they propagate across the tissue. Okay, so there is a large and stable propagation of new waveform across tissues. So the question that I was asking myself, so if motor units propagate across tissues while also preserving part of their size, why do some of the results do not match neurophysiology closely, as I showed you the first result? And we can see here very, very clearly, right, that the EMG is representative of the neural code movement. So one idea is that one hypothesis that we have is the composition is failing. So we know that it is obvious, right, because we only identify the larger units, and we know a lot about that. We miss the units that are deeper. But this, if we can see in the EMG motor units from far away muscle, from the same muscle, we should get a very good relation, right, of the physiology. So it makes no sense if you think about it. So what we did, we implanted, you probably know quite well already, so the thin film electrodes. So these are high density electrodes developed by Dario's lab, and this is like they give you an unprecedented view of the neural code of movement, and you can relate this to the surface EMG. And then we did that. Our hypothesis was, let's stick an electrode, let's decompose that, and let's see the signal, how it is at the surface. So we don't decompose the surface EMG, we only decompose the intramuscular EMG. And what we found, so these were all the move-ups from the intramuscular EMG, these are all ordered by the sides. You can see a quite good relation. But what was surprising is that when you look at the relation between the size of the motor unit, so the recruitment threshold, and the peak-to-peak amplitude, you can see a nonlinear relation now. That was, we never found this. And in the surface MG, it's even cleaner, this relation. So the idea that we don't find a nonlinear, an exponential fitting between size of the motor unit and the recruitment and the electrophysiological activity is due to the fact that we miss this unit, but we can get them. They are in the EMG, they are in the surface EMG. Yeah? So I think there is it's quite important for future research. And so what can we do more to get that? One hypothesis that we are facing now in the lab is, because when we look at the EMG, we always think in one dimension. Yeah. So we have so we put this is one intramuscular signal, and you have time here, and then you have a vector of time. And if we put an electrode, a two-dimensional electrode, we have a matrix. Yeah. And here we have channels against time, and we can create heat maps. Yeah. This has been done a lot. It's a very good see. It's very informative for many applications, physiotherapy application, for example. However, this is because we understand that, but what machine could understand, there is now the era of AI, a machine can understand things that human cannot. Yeah? And this is already seen this in many applications. But we need to feed the AI data that is better. This was a central hypothesis we have been exploring. And what you can create some tensors, so you can pack in one dimension all this information into one number. This number means nothing to the human, we cannot decipher it. However, a machine now has all the spatial-temporal information to depict that. And this is, it seems pretty relevant, especially when you want to explore unconstrained movements, like this one. And what we found here, that when you move, the AI embeddings seem to very close match the movement of the hand. So that, all this information in the EMG that is present at the monopolar level, it's there, and you can construct the movement of the full human hand, for example, and then study the neural structure that determine that movement. And this seems to be better than if you find motor units, but if you would find all motor units, these two, in my opinion, would be equal. But we cannot find all the motor units. But if you would, in theory, you can already see that. So all of these lines are basically the motor unit that are constructing a movement, and you represent them in a 2D space. But you can see that there are a lot of they are not very. They don't match closely the movement, which is a circular movement, because there are also motor unit encoding posture, for example, where the AI can remove those. Okay. So just as a summary for the first part of the talk, we are only capturing a small fraction in that individual of DMG signal content, and the result suggests that monopolar surface EMG is rich in information that we are not yet extracting. Now we will see some of these results applied to the neural control of upper and lower limb muscles. So there's been a lot of research here, so how the central nervous system controls all of these muscles, and here is the case. I think one very good example is that to compare the hand with the leg, because these two types of joints, they have really different anatomical constraints. So the leg innervates the same tendon, so that during knee extension, both vasti are inserted to the same insertion, while in the hand you have each muscle has its unique space. And what has been there for quite a while, that synergistic muscles, they receive one common input, that one signal goes to two synergistic muscles. And you can see here very clearly in the case of the hand muscle, so when you perform a thumb or index digit, and you take the manifold, this is the manifold of the two units, you can see that they are in the same manifold. They are highly correlated, so they are controlled with the same input. However, when we look at the leg, you see that some of these motor units, even if they are in the same muscle, they are not correlated. This is a linear regression, so this is quite a powerful tool to assess neural connectivity. And you can see this at the whole population level, that in the head you have these two projections, while in the leg there is a lot of the two common inputs that are shared and unique. So the question now that we were wondering, so can this dimension be separated from a person? If we take a human, can this dimension in the leg muscle can be separated? So because of the problem with crosstalk, etc., we tried to implant several intramuscular electrodes in the leg. So we implanted the 3 electrodes in the VL and 3 in the VM. So 1 in the proximal and 2 in the distal part. And so then we created this has been done quite a bit already in the literature, that you can create a neurofeedback with the intramuscular signal. So in this case we are very sure the target muscle, and you can see that you can ask the subject to see, during an isometric chair, if to explore this space. And so if you go here, for example, you would only activate the VL, and here only the VM. So when we look at the force signal, and these are all the intramuscular electrodes that are color-coded with respect to where they were inserted, you can see the ramp contractions, and you can see that all the MG, intramuscular MG, show very similar activation. This is a very low ramp contraction, at 5% MVC. After training, this is just after 20 minutes of training, subject learned to selectively control his feedback. So to activate either only the VL or VM. But what they were very able to do, you can already clearly see here, that all these channels were highly correlated. However, the VM proximal was the only part that all subjects could split. They could easily split this part, just after a bit of training. You can see here, so these are the 2 electrodes. You can see this electrode here and here. So these 2 electrodes show a very similar connection. But when you look, for example, here, there is a high excitation in the VM. In this side, so the proximal side of VM is almost silent. And this pattern we found it across all of our subjects. So when you look at the force feedback, it is the correlation among all clusters is very high. But when you selectively use neurofeedback, you can see that you can split quite well these 2 muscles. So this part of the VM in all subjects. And so this connection basically, so there seems to be a 1 muscle here and then 1 muscle there that is different. So we call it VM, but maybe neurally it's not VM. It is a different signal. And you can see here also the motor unit. If you decompose the intramuscular signal, there are unique motor units that are controlling the task. So now we know that in the past it seems that voluntary association is possible, but location specific. But what are the dimensions now if we go in the hand, as I said before? Now let's compare it to a signal that has more dimensions. And we know, the signal is also quite difficult. I will go quite quick here because the study is already published. But what we found here, we found that when you basically move the thumb and the ring finger and the big finger, these are the same neurons that are encoding this task. These are the tracked neurons. You can see that a large proportion of neuron is not present. If you look more closely, you will see that neurons that are not present are the neurons that are modulating the task. So there are some neurons that are highly encoding the movement of the hand, and some others that are holding the posture, this tonic firing. This is not surprising because the hand is like that, so they must destabilize the wrist. But there are some neurons that are unique that you cannot find in other tasks. You can see very clearly here. This is the task kinematics. And you can see here that the smoothed motor unit firing rate of this unit is encoding perfectly well the kinematics of the ring finger, slow and fast, then it's silent during the pinky finger, and this motor unit that is postural, that does not correlate very well with force, it's also in the other muscle present. So there are some unique neurons that encode the control of the hand. And this is pretty powerful if you think from a mind control perspective. If you find these neurons, you basically have the kinematics, perfect kinematics decoding. And this you see across all subjects that we split this unit between the prime mover and not prime mover, and you can see that the prime mover across all the subjects, so these units that correlate with movement have a very high correlation. How does this translate in the concept now of synergy? This was our central question now. How does this finding translate in the concept? So in Desmet, now there have been several studies, but Desmet in the 81 already proposed that there were several neural commands called the synergy cluster. So, but the idea is that you have several inputs that project to multiple pools of motor neurons and to the same pool. So one experimental protocol here that is very interesting is if you ask subject to do an abduction and a flexion, the first dorsal interosseous, here it's a prime mover, it's encoding abduction, and here it's as a synergist, because the flexor is the first prime mover. And so here you can clearly see in this experimental protocol, you can test the hypothesis if you have additional inputs that are different, that construct the movement. So we implanted again some subjects in the FDI, and we constructed a protocol where you could selectively control, explore all the space of the index. So you can go in a 3D space, and you can go around contraction in the flexion of abduction. And what we found is that when you look at the recruitment threshold, the recruitment order, in the same task, the motor units are very stable. As soon as you change direction, there is a swap of the recruitment order. So there are bigger motor units now that are recruited earlier and vice versa. So it means that the input is a strong proof that the input is different. But it's so much stronger that it can change the recruitment order. This means it's a really different input. That's the only way, because the science principle is there. This does not mean that the science principle is not there, but it's just that the input goes beyond the science principle. So, and this is the difference. That it's not a violation of the science principle, but rather a different input that creates a different recruitment order. So hand muscle neural synergy are more complex than previously assumed, and the neural control of the human hand operates on a high dimensional scale, with only a few motor neurons encoding specific digit movements. So the last part of the talk, 3 minutes, how does this translate into rehabilitation? So I said, I really think we are now in a good step where the EMG can be seen almost as a cure. Why do I mean that? So we found some time ago, there was a patient implanted in the brain with an electrode, and these electrodes can decode very well the dynamic of the hand. This patient was motor complete. You are only ethically allowed to implant patients with an ultra-array, so with an intracortical device if they are motor complete, that they have no movement. And they also developed this sleeve to stimulate the hand and also to record it. And what we found in this patient, this was now, it was 6 years ago, we found that there were some neurons below the level of the lesions that this patient could control. So even if he was paralyzed, when we asked the patient to move the hand, we found in this sleeve specific motor unit that were related to movement. And in this study that we had, this video, there were 12 participants, including 8 participants with the C4. These are motor complete, they cannot move the hand at all. So it's even some of them are sensory complete, so they have no sensation. We found that there were spared motor units detected for all of these patients, and they were also, like in our healthy individual, some were postural and some were modulating, very well modulating the task. And you can see here the number of motor units that is comparable to the subject, the healthy subject. And going back to the first slide that I was showing you, you can see some of them, we find a very large number. So in some of the motor complete, you can see a very large number of motor units that we can identify, because these are very few motor units present in the signal. And then the idea was, let's now try to make them control. So we developed an AI that can translate this electrical signal in real time. This is a mind control problem, has been done a lot in the literature, but now we developed this tool specifically for spinal cord injury, that the subject can look at a control hand that you change, that you can access. So you can change the frequency, the modulation about his hand. So you have now an interface with his brain. Because you don't know what the patient is doing, but you want to know that. So you can use this as an invasive estimation of brain activity. And then you can try with an AI to go from DMG to this. So you can see this patient, despite the paralysis, when we ask to flex the index, he can flex the index. And when we also ask the patient to change the activation, he can change it. So this signal present there, this is in real time is the best demonstration. So it shows that the patient has these control abilities. And also with real-time motor feedback, you can basically make them now do a virtual ramp contraction. So you can create a digital muscle here. Essentially, this is a digital muscle. We are taking the spike train and converting them with the motor unit, the spike train, and you can make them control that. So, and then we wanted to go, we wanted to really see, let's allow this patient to really now grasp again. That's our final goal. And we created this, it's a prototype of a soft exoskeleton that can make you, and enables the patient to, in this case, to do a pinch finger action. This was actually the first experiment with this patient that completely she lost the ability to use the hand. Now we've been training her, this is our last version, and we arrive at the stage now that they can even do a pegboard task. So, without this system, they could not do anything. Yeah? So now with using the EMG signal and connecting to a soft glove, they can perform a dexterous task. Yeah? If your pegboard is pretty challenging, even for healthy humans, to do it fast. But with this system, so this is not as a final cure, but it's a rehabilitation tool that we can get quite close now to really assist patients in a way that before was not possible. And I didn't put here because of lack of time, you can access to this manifold, to this dimension with AI and monitor rehabilitation very closely. Yeah? Because you know exactly here what the patient is trying to do, and you can track it. So you can monitor. So it's not anymore everything in unknown. The physiotherapist and the medical practitioner can have information to this dimension. So with this I want to thank you, and if you have any question, please go ahead.
Thank you, Alessandro. Thanks so much, impressive, and thanks for taking the time anyway, even if we lost a lot of time at the beginning. Okay, if there are no particular questions, maybe we can go on. Just a few words. There is in the afternoon will be a game. Okay, sorry. Yeah, you can use it.
Thank you. Very, very quick curiosity. Very impressive talk, Alessandro, as usual. I was wondering if you noticed or you already had the opportunity to monitor if there are also in the rehabilitation process like some differences in how motor units are evolving, or if you see in the rehabilitation part some regions.
So far we didn't really run a rehabilitation study yet, but we have I would say a training study where 3 participants they came for 9 times in the lab, and we trained them, and we found that the feedback it was much more precise, and this it was because they were able to recruit new motor units. So, but this was a very short intervention. I think with a longer intervention, also structural changes could change. So how more tasks they could perform. That's what we hope. So not just precision, but also more dimension. Yeah. Fine.
Thank you for the talk. It was very interesting. Did you get a chance to work with spastic sickness?
Yes. So in motor unit, so I didn't put because of lack of time, but So spasticity is a big topic, but just briefly, so when you take one of these patients, usually all these patients are very spastic, so the hand is fully flexed like that, and if you record EMG, you see a clear tonic activity of the motor unit, and these motor units are encoding the spasticity. So we see this a lot in spinal cord. A lot of motor units are spastic, and now we have been working how we could remove the spasticity. There are 2 ways. One, so that we have been working, and yeah, but it's a very interesting part, spasticity.
Based on the same concept, and we thanks also Alessandro and his group for providing us with some code. There will be a game in the afternoon where you can where you can play rock, scissors, paper, maybe it's not the proper order, based on the activity of the forearm. The algorithm will understand which is the movement you're doing, and so we try to use a scientific tool to make a game, but it's just a demonstrative tool.
Yes.
Thank you again.
So we go to the next speaker, that is Francois Hug. Francois Hug from Université Côte d'Azur, Nice.
Hi everyone, so thank you very much for giving me the opportunity to present our work. So hi everyone, thank you very much. So today I will present recent results where we leverage large-scale motor neuron recordings to provide deeper insights into the control of movement. And specifically, we are trying to understand the types of inputs that the motor neurons receive and how these inputs are distributed across motor neurons. So one of the main challenges in understanding the control of movement lies in the complexity of the human body, where we have more than 350 joints, more than 600 muscles, and in each of these muscles you have up to 700 motor units. So to understand the control of movement, we need to understand how the central nervous system controls this large number of degrees of freedom. And among the various theories of motor control, one suggests that movements are controlled through a combination of muscle synergies, where a synergy is defined as a group of muscles receiving the same commands. So it's what you can see on the right-hand side, where you have 4 synergies controlling the learning muscles during gait. So for example, the first synergy in blue is mainly composed by 3 muscles, which all receive this command on the right-hand side. This one. So the second synergy in red is mainly composed by 2 muscles, which all receive this command, etc. So muscle synergies have been proposed as building blocks that could simplify the construction of motor behavior. So in other words, by reducing the number of commands to specify, it is thought to simplify the control of movement. But there is one potential limitation in that muscle synergies are classically identified from bipolar interference EMG, where a single EMG signal is assumed to represent the activity of an entire pool of motor units. It means that this approach cannot reveal the control of movement at a thinner scale than the muscle scale. So, and we know from a long time that motor neurons are the finite common path for motor control. And so if you look at the number of motor neurons innervating the body muscles, you can see that there are about 200 times more motor neurons than muscles. So in this case, you have both alpha and gamma motor neurons. So it's pretty clear that the central nervous system is facing a much higher dimensional control problem at the motor neuron than the muscle level. So here you have a pool of motor neurons, and we know that these motor neurons receive both independent and common inputs. And it is these common inputs that enable an efficient control of muscle force. So without any common input, it would be very difficult, if not impossible, to control muscle force. So we know that there is a low dimensional control of motor neurons. They must receive a certain degree of common input. But what we don't know is how these inputs are distributed across motor neurons, or in other words, what's the smallest unit of control used by the central nervous system to control movement. So recently we introduced this framework where motor neurons are grouped into clusters, modules, synergies, based on the common inputs they receive. And very importantly, these motor neurons may involve only a portion of a muscle or span across muscles. So it's what you can see on the right-hand side, where you have motor neurons innervating the same muscle, let's say muscle 1, which are split in 2 different synergies. So one in green and one in blue. Conversely, you have motor neurons innervating different muscles, in this case, for example, muscle 1 and muscle 2, which belong to the same synergy. So as you know, motor neurons receive three types of inputs: inhibitory inputs, neuromodulatory inputs, and excitatory inputs. And we are interested not just in determining the type of input that the motor neurons receive, but also in understanding how these inputs are distributed across motor neurons. So to this aim, we take a reverse engineering approach where we leverage large-scale motor neuron recordings that we consider to be the neural code for movement generation, and we work backwards from this output to infer the inputs to the motor neurons. So to apply this approach, we need to decode the activity of a large sample of motor units, and we know that to increase the number of motor units that we can identify, we can increase the number of sources, so the number of electrodes, and in some cases we can also increase the density of the electrodes. So it's what we did in this experiment, where we used 4 grids of 64 electrodes on the vastus naturalis muscle, so a total of 256 electrodes. We did the same on the tibialis anterior, and on this figure you have a motor unit yet as a function of contraction level. Each dot is a participant, and you can see that in some participants we were able to identify up to 100 motor units in the tibialis anterior muscle and up to 70 motor units in the vastus naturalis muscle at about 20–40% of MVC. And interestingly, we were still able to decompose a large number of units at 70 and 80% of MVC. So the key is to increase the number of sources. So Alessandro presented this study. So they identified motor unit synergies in the vastus naturalis and vastus medialis muscle. So they applied a factor analysis on the smooth discharge rate of motor units, and they observed that two latent factors explain most of the variance of the signal. And importantly, motor units from the same muscle did not necessarily belong to the same latent factor. So it's what you can see on this figure, where you have, so each dot is a motor unit, in green from the vastus medialis, in purple from the vastus naturalis, and it does represent the weight of each unit in each of the two latent factors. And so you can see, for example, that in latent factor 1, you have a large weight for both motor unit from both the vastus naturalis and vastus medialis. But importantly, other studies report only one latent factor to explain the dynamics of motor unit activity in other muscles, for example, in the gastrocnemius medialis, soleus, and first dorsal interoceus. So, for example, in this study, we were able to identify an average of 50 motor units in the gastrocnemius medialis per participant, and an average of 40 motor units in the vastus naturalis. And what we observed is that the behavior of a motor unit in the gastrocnemius medialis can be captured by a single latent factor. It's what you have on the right-hand side, where you have the accuracy of the reconstruction as a function of the number of latent factors for each individual participant. So for the gastrocnemius medialis, only one single latent factor can explain the dynamics of motor unit activity. But for the vastus naturalis, you can see that their behavior is better captured by the 3 latent factors. So the question is, do these latent factors reflect neural constraints? Do they represent volitionally controllable drives? So to address this question, we can use an online control paradigm where we ask participants to volitionally dissociate the activity of motor units. And we consider that if they can dissociate this activity, these two motor units receive a low level or no common inputs. So to use this approach, we need to decode the activity of motor units in real time. So it's the reason why we developed this open source software, where you can choose the different types of feedback, for example, this one, where you have the activity of two motor units in a 2D space. And we ask the participants to move to the cursor represents the instantaneous discharge rate of the two units, and we ask the participants to move the cursor in one of these two target regions. And if they can achieve, if they can reach the target regions, it means that they can isolate the activity of these motor units. So it's what we did in this experiment, where we focused on pairs of motor units from synergist muscles, so the vastus lateralis and vastus medialis during the extension, and the gastrocnemius lateralis and gastrocnemius medialis during plantar flexion. So you have here an example of the feedback, so they had to reach target 1 and target 2, and very importantly, the lower threshold motor unit was always displayed on the x-axis, which means that a true flexible control is achieved only if the participants can reach both target 1 and target 2. And actually reaching target 2 means that the participants were able to isolate the activity of the higher threshold motor unit. So you have here an individual example, so two pairs of units. On top you have a unit from the gastrocnemius medialis and a unit from the gastrocnemius lateralis, and at the bottom you have a motor unit from the vastus medialis and a motor unit from the vastus lateralis. So here you have a strong covariation between motor units. So this data have been obtained during the reference contraction, where the only feedback which was provided to the participant was the top feedback. So they had no information about the activity of motor units. And here you have an online control task where we ask the participants to move a target in the two target regions. And you can see that this participant was perfectly able to isolate the activity of the motor unit from the gastrocnemius medialis or gastrocnemius lateralis. But the same participant was not able to isolate the activity of the VM or VM motor unit. And we observed exactly the same results on the 28 other pairs of motor neurons. So none of the participants was able to dissociate the activity of the VM and VM motor units. So what it suggests is that the activity of VM and VM motor units is constrained by common inputs, which is not the case for motor units from the gastrocnemius medialis and lateralis. And it shows or it suggests that this strong covariation that you have during the reference contraction is mainly driven by mechanical constraints. So in this study, we aim to determine whether the three latent factors that we identified in the vastus lateralis actually reflect independently controllable drives. In which case, motor units associated to different latent factors could be theoretically independently controlled. So you have here again individual examples. So on top you have two motor units from the gastrocnemius medialis, and on the bottom panel you have two motor units from the vastus lateralis. On the left hand side you have a condition where we ask the participant to move the target, to move the cursor in the target 1. And on the right hand side, you have a condition where we ask the participants to move the cursor in target 2. And you can see that this participant wasn't able to move the cursor in target 2, so there was no flexible control. And again, we observed exactly the same results in the other pairs that we provided as a feedback to the participants. We also explored the units which were not provided as a feedback, and we observed again exactly the same behavior, so very rigid control. So it demonstrates or it suggests that the latent factors do not necessarily represent controllable drives. So we ran simulations to try to better understand these results, and we observed that the multidimensional behavior that we observed in the VA can be shaped by spinal circuits, such that a single descending drive can lead to multiple latent factors. And our simulation showed us that recurrent inhibition can be a potential candidate for shaping this multidimensional behavior. Which is why we are currently interested in developing an approach to quantify recurrent inhibition in humans. So from motor unit spike trains collected over a pretty long period, so about 200 seconds, we construct synchronization cross histograms which represents the probability of firing of motor units at specific time delays before and after a reference motor unit. In this case, the reference motor unit is the motor unit in red, and at each firing of this unit, we quantify the time delays at which the other motor units fire. So from these cross histograms, we quantify the trough area and we quantify the peak height. And our simulation showed that the trough area is strongly correlated with the recurrent inhibition, and the peak height is strongly correlated with the high frequency common inputs. But the issue is that there is an interaction between high frequency common input and recurrent inhibition, such that recurrent inhibition also affects the peak height, and the high frequency common input also affects the trough area. So to distinguish, to separate the effect of recurrent inhibition from the effect of high frequency common inputs, we use a simulation-based inference approach. So first, we simulate spike trains with known level of recurrent inhibition and known level of high frequency common inputs. And from these simulated spike trains, we construct the synchronization cross histogram, from which we quantify the trough area and the peak height. So we run up to 10,000 simulations, and then we train an error density estimator to map these physiological features with the features of the cross histograms. And finally, we apply this estimator on our experimental data. So here we have some experimental data. We calculate from this experimental data the trough area and the peak height, and we apply this estimator, which gives back a set of possible values which explain or which best explain the experimental data. So it's very important to note that it doesn't provide a single value of recurrent inhibition and high frequency common input, but a distribution of possible values. So we are still in the process to interpret the data. So here are some preliminary data. So we collected experimental data on the first dorsal interoceus, gastrocnemius medialis, soleus, tibialis anterior, vastus lateralis, and vastus medialis on 6 different participants, and at 10 and 40% of LVC, so 2 different contraction levels. And so you should focus on the panel on the top left, where you have a distribution of recurrent inhibition, and we observe, so we also calculated recurrent inhibition between muscles, so we have homonymous and heteronymous recurrent inhibition. And you can see that heteronymous recurrent inhibition is lower than homonymous recurrent inhibition, and that recurrent inhibition in the FDI is lower than in other muscles, which was expected. But what is more interesting is the change in recurrent inhibition between the contraction intensities. So we were expecting a decrease in recurrent inhibition, which is the case for most of the muscles. So blue indicates a decrease and red indicates an increase. So in most muscles, we observe this decrease in recurrent inhibition with contraction intensity, except for the VL and the VL, where we observe the large increase in recurrent inhibition. As a result, at 40% of LVC, we are pretty large differences in recurrent inhibition between muscles. So the VL having the higher recurrent inhibition, FDI still having the lowest recurrent inhibition. But what is interesting is at 40% of LVC, heteronymous recurrent inhibition can be higher than homonymous recurrent inhibition in FDI or tibialis anterior. So we are still in the process to understand these between muscle differences in behavior. So if you have any inputs. And that, thank you very much to my collaborators. And we have a 2 years position, postdoc position open in Université Côte d'Azur. It's not always like that, but most of the time.
Thank you, Francois. Are there any questions? Okay, thank you again for your interesting talk.
So Filipe is from Madrid, from the Cajal Institute. I never able to pronounce Cajal. Is it correct? Okay. So thank you, Filipe, and thanks.
Hi everyone. Thank you. First of all, thank you Enrico and Andrea, the CEO and the whole team for inviting me. It's a pleasure to be in this beautiful place. So today I will share with you the preliminary results that we got in our group from a larger study where we are exploring peripheral electrical stimulation using a device produced by OTB, and it's in the upper limb. So in the past few years, we have been working with patients with essential tremor. For those of you who are not familiar with the disease, it's the most common movement disorder. As you can see here, it's one of our patients. They typically present postural and kinetic tremor. And this, of course, interferes in the activities of daily living. As a first-line therapy, they usually receive medicines, but they present limited efficacy. So for those the treatment doesn't work, they also have the option, some of them, to undergo deep brain stimulation or high-intensity focused ultrasound. But still, part of this population cannot undergo these treatments, or they simply do not want to take the risk because in some cases there's also the risk of dying. So that's why several groups, some of them here present, we have been developing non-invasive alternatives for these patients. This is a figure from a paper that we submitted now, a figure prepared by Christina, who is there. And so there are many techniques now that have been explored, and we are focusing on peripheral neuromodulation, namely using some motor threshold peripheral electrical stimulation. So this is a video, so an animation representing part of the task that our subjects perform. We ask them to outstretch the arms to elicit tremor, and then based on the real-time EMG information, we are able to deliver electrical stimulation, and this is using the device produced by OTB Electronic. So in the past, together with Dario, José Luis, and this was a great job done by Alejandro. We showed that a few minutes of stimulation led to great results, like after just you can see again, so after just 15 minutes of stimulation, this specific patient, she just stopped having tremor, and in some cases it lasted up to 24 hours. So since the beginning, our strategy is based on the hypothesis that we are actually modulating reciprocal inhibition by the alternating stimulation of antagonist nerves. We can then activate these afferent fibers, and there are inhibitory interneurons that will then decrease the activity of the tremorgenic burst. But this has never been assessed, as far as I know, and that's part of what I will present today. So I'm sure most of you know this secret. It's very, when we walk, that we activate soleus and then the tibialis anterioris inhibitor. We can also modulate it through electrical stimulation. So if we deliver electrical pulse here in the 1A efferent, it synapses with the alpha motor neuron that from one side it will excite the very same muscle. But there is also an inhibitory interneuron here that will inhibit the activation of its antagonist. So if we think that as this antagonist as being the muscle presenting tremor, in theory, we can reduce its activity. This has been, so this circuit is being truly investigated in the lower limbs, especially in the soleus and tibialis anterior. However, in the wrist flexors and extensors, there is no agreement. So some authors suggested that this is actually mediated by 1B efferents, which is another type of efferent fibers. Others have suggested that there is a convergent excitatory input from both types. And here we will test that from one side we can use electrical stimulation to modulate reciprocal inhibition in different directions, and that this reciprocal inhibition is actually mostly mediated by group 1A efferents. So again, just going back to the same schematics, that we can, in theory, reduce the activity of one muscle or the other. What we get at the end is that in tremor, it's a cyclical activation of a pair of antagonist muscles, because they perform this. So for example, the blue one is the flexor, the black is the extensor. So we can again use OTB electronic devices, record this in real time. It's always based on EMG, and we do recording windows and stimulation windows. There's no time to get into details, but this is mostly to avoid the stimulation artifacts, so we predict when the muscles will contract. So again, alternating activation of both muscles, and then here we would expect the contraction of the blue one, the flexor, and that's why you see these black vertical lines, which are artifacts from the stimulation of the antagonist following this strategy. And the same for when the black one is activated, we stimulate the antagonist. Okay, so we call this out-of-phase stimulation, and the opposite one is in phase, which would be the stimulation of the muscle being contracted. But we hypothesize that will lead to increase in tremor. So it's unethical to test it from our point of view. So in another study, we are just comparing with sham stimulation. But we can do this in healthy subjects mimicking tremor movements. So for that we use a very known probe, which is the H reflex, and which is the electrical analog of the monosynaptic stretch reflex. So when the physician hits the knee and with a hammer, and then you extend the leg. And then we use a paradigm, the test and conditioning stimulus to assess changes in reciprocal inhibition. So it's just a basic representation. If we stimulate the median nerve here, this 1A fiber as a connection to the alpha motor neuron, we got this H reflex, and if we increase the stimulation, the amplitude of the H reflex will increase, and then the alpha motor neurons will start to be activated too. They have a higher recruitment threshold, and then there is a moment that there is an antidromic direction. They go in antidromic direction, and they kind of reduce the amplitude of the H reflex until a moment that the H reflex is inhibited. Okay, and the M wave keeps increasing. So from one side, one part of the technique, we want to work on this ascending part of the recruitment curve. And then we also stimulate the antagonist to study this inhibition. So if we make these pulses to converge at the spinal cord, the H reflex will be conditional, inhibited. Okay, so at the end we have this red H reflex, which is unconditional, and we have the blue one, which is conditional. We can use a simple ratio, the peak-to-peak amplitude of both reflexes, and get we call it reciprocal inhibition ratio, to assess plastic changes before and after therapy. So that's our first hypothesis, that we can use electrical stimulation to modulate reciprocal inhibition. We first developed a platform that allows us to do this, like high-density EMG. So in the case of high-density EMG, studying this at the wrist is much more challenging than the lower limb. So here's an example of one of these subjects. He does he keeps the force constant, and in real time, every 5 seconds, we assess the H reflex and the conditional H reflex amplitude. Again, using this ratio, they do in different days in-phase strategy, which is the stimulation of the muscle mimicking tremor, and the out-of-phase, the one that we do with our patients. In this case, it's receiving in-phase stimulation. You can see here when the muscle contracts, this one the extensively receives the stimulation. And this was the first results that we obtained. So before and after in-phase stimulation, the reciprocal inhibition increased. So this ratio decreased because based on this representation, the conditional pulse is getting lower. It was more conditioned by the antagonist. However, when we deliver out-of-phase strategy, the one that we use with our patients, the changes were in opposite direction, as you can see here. So actually there was a decrease in reciprocal inhibition. So for this first hypothesis, we think that this supports this first hypothesis, that we can in fact change the direction of reciprocal inhibition using different stimulation strategies. And for the second one, which is much more challenging, we wanted to assess whether this is modulated by the activation of 1A efferent fibers or not. So here is a representation of muscle fibers with several 1A efferents. When the muscle is contracted, they do not signal any information. However, when the muscle stretches, they signal this information to the spinal cord. And we can do this using, we can do this with electrical stimulation during the analogy. However, the problem is that the recruitment threshold for 1A and 1B efforts is similar, so in theory, they can both be activated by electrical stimulation, but we know that vibration over the tendon increases the recruitment threshold for 1A efferents. So we can use this to see, so after vibration, some 1A fibers will be silent, so we hypothesize that only those that can be activated with lower recruitment thresholds will signal this information. So if 1A efferent have a key role in reciprocal inhibition, we also expect to see this in our assessments after vibration. And the final results of this study, so again, this is what I presented before, without vibration, increase in reciprocal inhibition, so decrease in this ratio. But it's very interesting that after vibration, the reciprocal inhibition decreased to 22%. The same with out-of-phase. I showed this before. It decreased after therapy the reciprocal inhibition. But after vibration, there is like a summation of the effect after vibration. So it's much more pronounced. And then in the 5th day, so they were really tough because they underwent 5 days of experiments to do these different strategies. And vibration alone also lead to a decrease in reciprocal inhibition. So we still don't know if this is by chance because the sample size is still small, but this is super interesting because if we look at out of phase without vibration and vibration alone, if we sum both, they equal this one, which suggested that there is a summation of the effects. And we also think that this supports our hypothesis that at least using our stimulation strategy, this can demonstrate that reciprocal inhibition is mostly mediated by 1A efforts. So to conclude, and all of us can have lunch, so reciprocal inhibition at the wrist level can in fact be modulated by some motor threshold peripheral electrical stimulation. When we deliver in-phase stimulation, we increase reciprocal inhibition, and when we deliver out of phase, it decreases. On the other hand, we also showed here that the vibration seems to decrease the reciprocal inhibition. This is in line with previous reports, also showing decreased spinal loop and motor neuron excitability. Since after vibration, less 1A afferent fibers can be recruited, the effects of our stimulation strategy seem to have a cumulative effect. And overall, we think that this demonstrates a key role of 1A efferents in reciprocal inhibition, and we also will assess that, but we think it's the same in our patients with essential tremor. And this, of course, has implications for trauma management, that novel strategy will be explored after this, including vibration and stimulation. So I want to thank my lab members, all collaborated directly or indirectly of any part of this work, to the funding entities. If I just have 30 more seconds. So some of us here present, we developed the biomedical engineers pledge, which is similar to the Hippocratic oath that the physicians and products when they graduate in medicine. This was led by Anthony Boder. So if you have curiosity, you can just check the QR code. It will be published in a couple of days. But basically, that every biomedical engineering student that should come into guarantee the safety, health, well-being of our patients, and hopefully this will be disseminated in more universities around the world. Okay, thank you.
Thank you, Filipe. Thank you so much. So we are close to lunch. We just still have a couple of videos. I will not explain too much, but it's...
Now I would like to introduce Josè Pons for Silvia Rio Reliability Lab, Chicago.
Okay, thank you so much, Andrea and Rico, for inviting me to be here with you. For me, it's a pleasure because I think we started collaborating back in 2010, around 2010. It was in the framework of the Tremor project. I remember that Dario made a connection with OTB Electronic. At that time, we needed specific development thrust. that combine both EMG recording and stimulation for our tremor suppression studies. And we started with that collaboration. And I will say that roughly 90% of the studies that we run in our lab are using your product. So this has been a successful collaboration so far. So because my primary affiliation is the Children and Avrillon Lab, which is the former Rehabilitation Institute of Chicago, I will be speaking about how we can use EMG-derived biomarkers to close the loop with interventions for neurological populations. So since I moved to Chicago 6 years ago, my research has been mostly translational, so trying to use the technology to improve the interventions that we have in our system. So basically today I will be speaking about how we can use EMG in a clinical setting for use every day in order to close the loop for these conditions. So this is going to be the outlook of my presentation. So first I will speak a little bit on the impact of stroke, which is the primary population that I will be focusing on. And then I will address specific intervention that we have been developing and running for already 2 or 3 years now. And then I will summarize with a few take-home messages. So let me just give you a little bit of the background. So a stroke, as you know, is an acute neurological disorder that is motivated by a disruption of blood flow to the brain. So it is very prevalent, and the incidence is huge, and it is accelerating in terms of the number of patients that we have. So an important thing is that roughly 80% of post-stroke survivors have gait impairments, and 50% have balance impairments. So this not only impacts quality of life, independence, and so on, this also leads to secondary complications such as diabetes and other conditions that we need to try to avoid. So without going too much into the detail, today I will be focusing on strokes that have a primary impact on the corticospinal tract. So in these conditions, what we have is a disruption of this tract that is the one that crosses over to the contralateral side of the spinal cord and activates directly the motor units that generates our muscle. So in addition to this corticospinal tract, we have also the cortical bulbar tract that also crosses over to the brainstem and stimulates those of reticulospinal tract that inhibits the activity in the spinal tract. So because this tract is also affected because of the stroke, there is an imbalance on the inhibitory and excitatory inputs to the spinal cord due to the inhibition here. So as a consequence, we have first a reduced neural drive that is reaching the motor units because of the disruption of the corticospinal tract, and then we have this imbalance that promote the use of secondary tracts, such as the reticulospinal tract, that are in nature more diffuse, and instead of targeting specific muscles, target groups of muscles. So this has a consequence that we have a loss of independent joint control. Okay, so in addition to this, of course, there are many other issues related to stroke. So we have peripheral changes. So we have, for instance, muscle atrophy. We have loss of some of the sensory feedback coming back to the brain. So sensory motor integration is also affected. And then we have just an example of one of our subjects in the lab showing a classical pathological gait pattern with the affected and with the non-affected. So the picture that you saw, the video that you saw, is how therapy is being implemented in the lab. So basically, what we do or what the clinicians do, they rely mostly on qualitative and subject assessments instead of measuring biomarkers related to the condition of the patient. So we thought that we should try to develop data-driven approaches so that we can personalize the treatment plans based on biomarkers that we could use. Now, remember this scheme with all the pathways that were affected. So there is no today there is no practical way of getting information on what is happening with the different drugs in the clinical setting. So EMG is a good proxy of what is happening, because at the end what we have is the output of the neural driving in the muscles. We can record this activity, and this integrates all these impairments that I was discussing before. So the idea is try to use EMG to get measures that are patient-specific, that are actionable in the clinical setting, so you can use them in the clinical setting to enhance stroke rehabilitation. So now high-density EMG has been running already for a few years, so even though it is a relatively new technology, there are already a few studies with this population that looked into how the motor unit activity reaching the muscles is affected by stroke. And here you have just a few examples of different muscles where there is a clear reduction in discharge rate in the affected limb of these post-stroke subjects with respect to healthy controls. So in general, these studies are only limited to chronic stroke. In general as well, the studies basically focus on discharge rate as one of the measures to identify impairment, and has not investigated in the acute phase. So we have been running in the lab, and this was started by Simon, who is also here in the room. We started with a few studies where we were looking at how stroke leads to changes in the activity of the muscles. So this one in particular, I will not go into details. I will just use a couple of slides. But basically, we were looking at post-stroke subjects. We looked at muscles responsible for plantar flexion, and we wanted to see not only the discharge rate during the plateau of troposcapular isometric contractions, but we wanted also to see how, through correlation studies, how the common drive to the motor units could be identified intramuscularly and intramuscularly as well. Okay, so and then we wanted also to compare all these metrics across limbs, so affected to non-affected, and then to controls. So in a nutshell, what we observed is that in general we have a reduction of intramuscular correlation for most of our plantar flexors, and we also observed that there is an increase in intramuscular correlation, meaning that muscles that these muscles are getting common drive when they shouldn't be getting this common drive. And this is just a consequence of this diffuse innervation of these motor units. So, so it was very timely that you show these two videos where you can accelerate the use of high-density EMG. But in practical terms, with the 5 minutes that we have to get our subjects prepared for interventions, we are not yet there. So we need to look for alternatives to high-density EMG. And one thing is just looking at EMG. at EMG at all the different muscles that we are interested in and see whether we can get patterns of pathological activity that we can use to close. So this is just an example in the lab where we are recording activity from these post-stroke patients. Relatively, I think we have 16 muscles that are being recorded here, and then you can look at comparisons and try to look at metrics of how they work. Because sensory-motor integration is disrupted, one of the consequences of stroke is also loss of coordination of muscle activity. So for instance, we can use muscle synergies as a way of looking for parameters that we can use to close them. Okay, so this was my introductory part. Let me go directly to the main part of my talk, which is to discuss how we can use muscle synergies recorded from our post-stroke subjects to personalize an intervention and to use it in the clinical setting. So muscle synergies, I mean, you all are familiar with this. These are very stable across subjects for different functions. So these coordinated muscles have functional meaning. So for instance, we have synergies related to propulsion. We have synergies related to leg swing or to weight acceptance. So we can identify by looking at how these synergies in post-stroke subjects are modified to the specific functional impairments that they may have, and try to close the loop with this. So what the idea here is to get these synergies from controls and from stroke, and then compare them, identify which of them are impaired, and then use this to reconstruct, and I will come in a minute to this, functional stimulation patterns that are specific to that particular patient. So in the case of post-stroke subjects, it was published already many years ago that there is this merging of synergies. So the complexity of the complexity of the motor control is reduced. So the number of synergies is reduced. Typically, healthy volunteers have for walking have 4 synergies, and then we have many patients with 2 or 3 synergies, and a few with 4. So the idea is to try to use this as a way of driving the intervention. So. Then we can close the loop with any intervention that allows us to have specific assistance at different joints that we will personalize based on the synergy analysis. So we have chosen functional electrical stimulation, but this could be closed the loop. The loop could be closed with, for instance, exoskeletons or any other tumor. So the idea is of using functional electrical stimulation. It's not that we, not only that we support the motor output to the muscles, we directly stimulate over the motor threshold, but this also provides sensory feedback that if this is timed or synchronized with the user intention, then this has been shown that improves neuroplasticity. So, in addition to this, FPS is currently used every day in our clinics for foot drop. So the idea is to improve functional electrical stimulation systems with multi-channel stimulation, with patterns of stimulation that we compute from the pathological synergies of our subjects. Good. So for this. You need to have something that you can implement in a patient in a few minutes. Okay, so for functional electrical stimulation, we are using these slips that integrate already electrodes for the muscles that we are targeting with this intervention. So the idea is to like I said, record EMG activity from our post-stroke subject. Compare them to normative data that we collected and stored for this function. Then we compare them and identify which of them are impaired, and the criteria for identifying impairment can be based on the spatial distribution of the synergies or the time activation of the synergies. And then once we have identified which synergies are obtained, are impaired, then we use a reconstruction to build stimulation patterns for the different muscles, and then we close them. So this is the study design that we have been using. So as a control, we're using standard of care, which is kind of high intensity gait training, similar to what you saw in that video. So our experimental group is high intensity gait training plus this synergy-based multi-channel FES strategy. So we have 6 weeks with 3 days per week rehabilitation. So this, then we had a baseline assessment, we had a post-assessment, and then 1 month follow-up. In total, we had 14 stroke subjects that we randomized to these two groups. Again, this is the group allocation. This is our intervention, and this is the control intervention that we are using, high intensity gait training. Just for you to see a little bit, this is our physical therapist setting up the sleep that I was showing before in one of our patients. The second video shows the calibration procedure for the stimulation. So we look at maximum stimulation intensity per muscle that is comfortable for the user during the therapy. And then we have a regular treadmill-based training without and with stimulation. Okay? So in terms of the outcome measures that we are assessing here, we look at clinical assessments, of course, 10-meter walk test, speed, 6-meter walk test, endurance. We look also at possible changes in the structure of the muscle synergies due to the intervention. And like I said, for comparing to normative data, we use both comparisons of the spatial distribution of the synergies and the timing through cosine similarity and cross correlation. So this is just another example of another subject training. So this is without stimulation. This is the first training session for this patient. Okay, good. Very quickly to the results. So in terms of walking speed, what we saw is that both groups improved from baseline to mid-assessment, post-assessment, and follow-up. In terms of the endurance, so the 6-minute walk test, only the experimental group showed significant results from pre to post and from pre to follow-up. So, but the important thing is that if you look at the type of, if you look at the samples, sample that we have, so this is the speed of all our participants at baseline. So you have a big distribution of walking speeds, meaning that we have household ambulators, we have community-limited ambulators, and we have also community ambulators. So the range was huge. And this is the limit, which is 0.4 meters per second, that separates the household from the rest of the subjects. So if you remove those 3 or 4 household ambulators, what you see is that in both speed and endurance, only the experimental group showed significant improvement. So this is showing that probably the intervention has to be it's not working for everyone. You have to be using the intervention for the right subpopulation in the stroke population that you are using. And it seems that for limited community and community angulators, this works. We are also looking at the minimum clinical importance difference. And when you compare the experimental group in terms of walking speed and endurance, for endurance, 4 out of 5 reached this clinical minimal importance difference, and they were always bigger than in the control group. So we looked at sign similarity and correlation, so we didn't see any change. Any change in the spatial structure of the synergies, but we saw a change in the timing of stimulation. So the other thing that we wanted to check is that whether this is something that is feasible in a clinical setting. So this is so we involved in this study 4 PTs, so they were trained, and then they were running all the experimentation that you saw. So they were putting this in, they were calibrating the system, they were running everything. In general, what we observed is a learning curve. So after roughly 8 to 9 sessions, most of the or all the PTs were able to set everything in less than 5 minutes, which is something that can be considered for a clinical implementation. So very quickly to conclude, so we saw clinically meaningful improvements in walking speed and endurance due to this new intervention that is based on EMG, on this EMG biomarker. The muscle synergy timings became similar to those of neurologically intact people. There were no statistical differences between groups, but based on the size effect that we from this study, we estimate that with 20, remember that we only had 14 subjects. With 20, we would reach statistical significance between groups. As a summary, I think we need data-driven precision interventions to reach the gap that I was showing in terms of having only subjective interventions in the clinic. I think EMG is the right way to go because it is a good proxy of what is happening in pathology and is clinically available. There are many biomarkers that can be used or derived from EMG. I was just focusing on those related to the synergies, but there are many. They have to be actionable, otherwise you cannot use it in the clinical setting. And the example that I was sharing, I hope that convinced you that EMG can be used to derive a metric, to close the loop with, in this particular case, with functionality estimation, but we need more power studies to establish effectiveness. So with this I finished. I would like to mention that everything that I discussed today was part of the PhD thesis of Jackson Devine that defended his work just a few weeks ago. And this is just some of the funding that we used for these studies. Thank you.
Thank you so much, José. Okay. Thank you so much, José. We know that you are leaving. Yes, probably. Is waiting for you. So I don't know if someone has a really quick question, otherwise we. Okay.
Thank you. Thanks for your talk. So one quick question about the normative data of EMG that you showed, because in your, in the clinical protocol you said that EMG of subject was compared to normative data and then used to compute the level of assistance. So how crucial is the choice of normative data? Because of course for lower limb there's less variability probably in gait with respect to upper limb, but still also, as you show, healthy subject have a different number of synergies. So how do you choose this, and how it is crucial for the protocol?
So we had, so we tried to replicate exactly the same training conditions that that we had for our postdoc subjects. So there was, so they were walking at slope speed. So we had our healthy volunteers walking at the same speed, and then we collected the data, and then we used, we extracted the synergies, and these are the ones that were used as normative for comparison to the post-stroke population. So, and then we did this comparison in terms of both the timing of the activation of each synergy through the correlation, and then also the spatial comparison with respect to the similarity. I don't know if this answered.
Yes, but my question was related to the fact that there's variability also among healthy volunteers. So depending on how much people you collect, we have probably a different normative band.
Yeah, but this is you're right. There is variability, but I think we included 15 healthy volunteers, which is I think more than sufficient to have a good set of a representative set of healthy volunteers. In the past, with Dario and with others, we did studies where we changed speed, for instance, slope, and the muscle synergies that we could compute across different conditions was very similar. So we are pretty sure that the data that we have is data for comparison.
Yes, okay, I have two.
I was curious about the technical detail. The sleeve with electrodes for stimulation, and also the programmable stimulator. Is some prototype that you made, or both?
So this was a collaboration with another industry in the United States, Psionic. I can send you the details. So they had a clinical collaboration with our hospital. So and then what they did is they modified slightly the sleeve for us, because we were, for instance, interested in stimulating also the gluteus medius, and they didn't have that electrode in the sleeve. So they modified this for us, and they opened the control structure for the stimulation of the electrodes to us, so that we could program the new intervention.
Another one, yes, I'm coming.
Thank you. I didn't quite understand which muscles exactly were you simulating inside the synergies, and also did you see any improvements in the synergies themselves outside of the intervention after the exercise?
So, So I was looking for. So these are the muscles that we were using. So gluteus medius, this is femoralis, semitendineus, gastrocnemius, the femoris, tibialis anterior, and vastus lateralis. So these were the muscles that we used to compute the synergies, and also the muscles that we used for stimulation. And we observed changes in the average number of muscle synergies in our population, but this was not significant, statistically significant. The only statistical significant difference that we saw was in terms of the timing of each of the impaired synergies that were used for reconstruction and to build the stimulation pattern.
Okay, so once more, thanks so much for that as the last presentation. And I think the presentation has been modified based on the vibes of the 2 days. So probably Dario has adapted a little bit the presentation
depending on what he saw yesterday at least. So please welcome Dario Farina, Imperial College London. Thank you.
Good morning, everybody. Thank you, Enrico, for the nice introduction. And thank you, Andrea and Enrico, for organizing this event, inviting me. It's nice to be the last in some ways. It's also difficult because we have heard some excellent lectures in these 2 days. Indeed, I had to put the slides together yesterday evening after removing all the topics that we have already heard about that have been explained brilliantly by previous speakers. So I have decided to select some advances in EMG technology. So the first part is snapshots of advances in a number of topics. This will be literally 1 or 2 slides each. I will not go into details. It's just to provide some information on things that we have not discussed in these 2 days, and that our labs and others are developing. And this will be related to modeling, to the analysis of spinal loops, to electrotechnology and interfacing. And then I have decided to give you some discussion on advances in bionic reconstruction, specifically the merging of neurosurgery together with interfacing is something relatively new that we have done in our laboratory that I still not covered. So, as I said, we start with the snapshots. This will be very short and with no details. So the first thing that we are not discussing these days is the role of EMG modeling, which I think will become more and more relevant in the future. We have very recently the possibility to basically build the digital twins of EMG generation. In recent papers, it has been possible to simulate EMG signals recorded with any type of electrodes realistically, with reconstruction of limbs from MRIs, so solving the biophysical problem in a very, very accurate way. And it is also possible to merge these models with biomechanical models and even with reinforcement learning algorithms that allow us to generate movement. So one important aspect in the next few years, in my opinion, will be the possibility of really generating movement in a very, very accurate way from a mathematical point of view, generating the EMG and the motor neuron activation in biophysical realistic ways, and generating EMG signals that are basically identical to experimental signals. So here you see an end moved with reinforcement learning. This is things that we are doing with Meta, and I will tell you in a second why. And at the same time, you have the generation of the motor neurons that produce these movements and the muscle activation and the EMG. So in this case, you can, I think, in the near future, literally have a digital twin of subjects. You can have variety of these digital twins, variety in anatomy, variety in neural strategies, and these methods, for example, can be used to train human-machine interfacing without having to recording calibrating signals, or to train algorithms without having to record again training signals. For example, you can teach an AI algorithm to decompose a signal without training by generating millions of these signals of digital twins that represent a very large population. And then you have a generalized algorithm that can decompose any subject in any condition online in a very fast way. And these things are really happening, meaning that they will be published in literally a few months to a few years. So I think the role of modeling will be very important, more and more important. We will not discuss this today, but it will be one of the great breakthroughs in terms of being able to understand the physiology, the neural control of movement, and being able to reverse engineer with artificial intelligence and understand mechanisms that we are not able to understand by the classic experimental way. Another aspect that I wanted to mention, this is mainly because we've been working a bit with people expert in spinal loops, is the possibility, because we have population of motor units decoding, to study better and better the spinal circuits with respect to the past. We can, for example, record motor units, and then we can stimulate. In this case, is a painful stimulation, cutaneous painful stimulation, and so you analyze the so-called cutaneous silent period, but you can do it with any other kind of spinal circuit. You can record the population of motor unit, and then you can build a post-stimulation histograms or post-stimulation frequencograms. That means how the frequency of the motor unit change after the stimulation. And because now we can record hundreds of motor units, so we can look at the differences that for which each motor unit is integrated in that specific input. So this is data from a paper that is appearing actually in a few hours, so if you're interested in spinal circuits, it should appear today. And this is work from Alessandro, who was in London for a period and now he's back in Spain. And here you can see that for each subject you can study motor unit by motor unit, for example, the duration of the inhibition depending on the firing rate. We can do it subject by subject, we can do it motor unit by motor unit. We don't need anymore to cluster a large amount of data into only population data. We can do that at the neurosubject level. Not only, but we can also, as I say, build very accurate models, in this case model of the spinal circuits. We can reproduce those results. So these are results in a number of simulated subjects in the same kind of experiment as before. You can match exactly the experimental result, which means that you can identify parameters of the model that tells you internal variables you cannot measure in this subject by matching experimental simulation data. All right, electrodes, again, very quick snapshot. Electrodes, we've been working for many years on intramuscular microelectrode arrays. The first paper, 2008, I was in Denmark. These electrodes that are small filaments, they are micro-machined. You can make them high density, they go into the muscle, they're very small and very thin. In the first paper I was in Denmark and I collaborated with people using these same devices for recording from nerves. But then we had the idea to use the same kind of matrices a bit modified to record from muscles. So this is a system that we developed some time ago. It can be inserted with a needle. You can have a number of platinum electrodes, at the moment up to 40. The interesting thing is that now we have imported the full fabrication methods in Imperial. We can do that fully at our university. We have substituted a number of the difficult parts in the photolithography with laser etching and ablation. We're not going to detail. So this can be produced much faster, much cheaper. And soon we'll have approval for this new series of electrodes. Here you can see a wafer. This is fully Imperial College. It's produced mainly with laser ablation instead of classic photolithography. And we are able now to have this kind of electrodes with attached to hundreds of recording points in a single array. And that's something very exciting for us. Here you can see another advance. This is from Sant'Anna in Pisa, the full technology. They're working with us to testing this, but the technology is theirs. Also, OT is in contact with them, so this will be, I'm sure, the version 2.0 of the simul-tattoo current version. These are real tattoo. As you can see, they are amazing systems. They are placed, I don't know if you know the tattoos of the children, that you place on the skin and then you put water on top. They are literally placed in that way, in a few seconds, and they can adapt to curvature of the skin, they can adapt to movements, and the signals are excellent. We are doing the composition in dynamic contraction with this system. They are fantastic systems. It's really just testing them. As you can see, they can adapt to conditions where the classic arrays will never work. So I think in the future, literally a few years, we will see, for example, commercialized by IoT systems like this as the immediate further development with respect to the system you will see this afternoon. All right, finally, for this snapshot, interfacing you've seen yesterday Alessandro did a very nice presentation on interfacing spinal cord injury patients. things that we did together partly in the past. Now we have a fully implanted interface in a spinal cord injury patient. So these are the micro electrode arrays as shown before. So we have spinal cord injury patients who have several of these micro electrode arrays implanted in the forearm. This is a very simple procedure. It doesn't bother the patients at all. It can be done relatively quickly. At that point, you have hundreds of intramuscular channels into the forearm, and then the patients produce the movement. The patient's fully paralyzed. There are only a few motor neurons surviving, a few tens. And the idea of having so many channels is that wherever they innervate the muscle, you can get that activity. And indeed, here you can see intramuscular micro-electrode array recordings from different individual finger movements, and you can see different motor units depending on the finger movements. And this is the composition of everything we can find in one of these patients. A lot of motor neurons active depending on the task. You can identify single finger movements. You can, in principle, have in these patients going back to playing piano if you have a sufficiently good exoskeleton or electrical stimulation. A final thing on interfacing, to finish with this very quick, as I call the snapshots that I would like to discuss with you, but just giving you the hint, is that we have talked a lot about spinal interfacing, and so getting the output of the motor neurons, but and we also have some hints from Francois and from Alessandro. When you get the output of a system, you can infer at least partly the input. You can infer the input, not only the input coming from spinal circuits, but you can also infer the input coming from the cortex. So out of the output of the motor neurons, you can estimate the cortical oscillation, for example, in the beta band. And we are doing that, and this is extremely exciting because it's equivalent to have a brain interface with a recording from muscles. So you have a cortical oscillation, for example, in the beta band, going all the way down to the spinal cord, going to the motor neuron output that you can decode from the motor neuron output. And if you are interested in going deeper in this, we just published a perspective in Nature Biomedical Engineering proposing this as not only a brain interface, but also José talked about biomarkers, also a method for biomarkers in pathologies. For example, the beta band is suppressed in stroke, is altered in Parkinson. You can monitor that just placing a bracelet on the forearm or on the leg, which is, in my opinion, amazing because it really means reading the brain, but literally, not in a general way, reading the brain by recording from the muscles. So our body is a screen of electric fields that even provide you information about cortical brain oscillations. All right. So these were just some complementary information in terms of technology, since we are in an event that is mainly based on technology that I wanted to discuss, that I thought is a good complement to what we had yesterday. And now I would like to tell you something about a bit more specific study that we are quite proud of, and this is specifically related to a topic we heard yesterday, which is control of bionic limb. Christina has given an excellent presentation yesterday on this topic. So the classic way to control bionic limbs, as you know, is also one of the classic uses of EMG. You record EMG from the stump of the subject, and then with any pattern recognition, you associate this to movement of the robotic arm or hand or leg. So there is a paradox though in this kind of approach, is that the higher is the amputation, the less muscles you have to interface, obviously, not only, but the higher is the amputation, the less natural can be the interface. If you have an amputation that is transradial, you still have a lot of extrinsic muscles that naturally control the end, but if you have an amputation at the shoulder level, you basically have normal muscles that naturally can be activated to infer the intent to control the end, right? So there is a bit of a paradox because exactly when you need control, you don't have any more muscle to do that. So as you know, you can solve this problem in various ways. One way is that you can put the microelectrodes in nerves, and this has been done for decades. Now it has almost abandoned as an approach in terms of decoding intent because it's very complex. The other possibility is a smart surgery that has been literally invented in Chicago, in the place where Josè Pons works, 20 years ago by Todd Kuiken. It consists in taking the nerves of the stump and moving them above in order to innervate the muscles above the stump. Now, when the nerve now fires to control the missing arm, the neural information goes to, let's say, the biceps in this case, and it will activate the muscle, and then by reading the muscle, you can infer the activity of the nerve. So basically, you use the muscle as a biological amplifier of the nerve activity. Instead of recording from the nerve, you put the nerve closer to a biological amplification, which is the muscle fiber, and then you read muscle fibers. And you read muscle fiber, it has a much better synchronization. And then you can interface it with classic EMG. So this is a video from long ago. I was in Germany working with Dr. Bock and others, and this is one of these patients. He has eye-level amputation, as you can see. 6 months before these measurements, he had an operation for which the main nerves innervating the missing arm is being redirected when you see the coronary maps. And the coronary maps are EMG recorded with high density recordings from the company team. So now you can see when the subject performs a certain movement, and now you have the different maps lit, they correspond to the different nerves that are sending information to the muscle, and of course now you can record from these maps and build a simple interface that can control a robotic leg. Alright, so this is well known, it has been done for a long time. Now there is an issue with this approach, is that if you innervate a polyfunctional nerve, so a nerve that is bringing a lot of information, a nerve that is mediating a lot of tasks, with this approach you send this nerve to a muscle and then you record a single EMG signal. So if you have multiple functions, you record one EMG signal, which is the summation of a number of different commands, but you can use it only for a single command. So each time you innervate a muscle, then you record the EMG and you get one command. So the question is how to get more signals. How can we really get all the information about this nerve? And one answer, which is not ours, is surgical again. You can complicate the surgery. This is Paul Sedell in Michigan, recent 2020, taking the nerve, cutting it in parts, and then connecting a muscle graft for each nerve. Then you record from each of these muscle grafts, and each of those muscle grafts hopefully will represent a different command. Of course, you don't know surgically what you are dissecting, but on average, you get more command than a single command. So this can be done clinically already, and this is an example of this surgery. So here you see a large nerve is split in 3 parts. Then you can take a piece of muscle from another part of the body and you wrap it around the 3 nerves, and then you can put, for example, intermuscular electrodes, and you get a signal for each. Okay? So this is great. This is great work. This is state-of-the-art in prosthesis, the frontier work in prosthesis. But we thought, why do you need to do that after all? I mean, you would have the same question after having heard all the presentation of these days, right? Why do you need surgery to separate nerves when we are able to separate motor neuron activity from muscle activity, right? So the point is, why don't we just record? Why don't we just have this polyfunctional nerve innervating the muscle? There will be many motor nerves for many different tasks, but we can decode them and go back to the actual motor neuron activity. And in order to be sure that you get all the compartments, because the innervation is scattered in the muscle, you would better do that with intramuscular electrodes, and so these are the arrays I've shown before. So we say, let's use these arrays. These are, as you can see, around 2 centimeters long, 40 40 electrodes, and in the future they can be implanted. This is a different technology, but it's just to show that you can also have a fully implanted version in the future of this system. So this was some years ago. We tested this idea of having microelectrode arrays in animals, separating the activity from different motor neurons in nerves that were innervated muscles. So this is an animal model of a reinnervation, as you can see, of the lateral end of the biceps for a nerve that was initially innervating the pole, the end of the rectum, transferred in the biceps, and here you can see the microelectrode arrays that are recording a number of intramuscular energy channels, and then you go back with the techniques we've seen today. You go back to the motor neuron, so you go back to the spinal cord, you get any function that is coded there. So this was some years ago, but then recently, and this is the work of Laura, who is around here, just as said in Nature Biomedical Engineering, we have translated that to humans, and humans has been particularly exciting because now you take a polyfunctional nerve, you connect it, and now you have a muscle that reflect, you see different colors, reflect motor neurons having coding completely different tasks, right? And now, so in the muscle, now you have compressed the activity of multiple functions. And the innervation is random, so you don't know where they are, these motor neurons, obviously. But then you can put, as you can see, this microelectrode array, so you can put one or more, and this microelectrode array, as you can see, will record the activity of the motor neurons, and we record the activity of motor neurons coding different functions. So that was the idea. So the idea again is to have this microelectrode array. You have the muscle that is basically the muscle has been artificially compartmentalized, right? But in a random way. And now you disentangle the motor neurons in the spinal cord that have arrived to that muscle. So this is one of these patients. This is the implant. As you can see, the small red dot. That's the microelectrode array inside. This is the microelectrode array. And these are a number of patients from where you will see a few results in the next few minutes, and then I will finish. So here you can also have an idea of the nerves that has been transferred, and here you can see the microelectrode arrays in a number of conditions. So these are typical recordings from this patient. These are 4 channels of the microelectrode array. They're very clean. They can be decomposed online with perfect precision. You can also guess the territory in the muscle if you are interested in, because you have the array. You can have the amplitude of the action potentials. You can build the histogram of the firing activity, and of course you can study the motor neuron over time when the patient is performing a certain task. So this is an example of a number of tasks, a number of reinnervated muscles, and you will have some motor units that are independent for each task, some motor units that are shared among tasks, and this reminds you the concept of motor neuron synergies that Francois has presented yesterday. So you expect that there are some shared units, some units are specific for the task. And indeed the interesting part of the study actually comes now and connect to the presentations of yesterday. So here we have all these functions directed in the muscle, but we expect that the nervous system still sees that control in a normal way. And what does it mean in a normal way? It has to send common synaptic input to cluster of motor neurons that are exactly those that Francois defined yesterday. So the nervous system doesn't know that this nerve is going to only one muscle and for which you are recording, and so we assumed or we hypothesized that we should find cluster of motor neurons, and because they receive a common synaptic input, we should be able to find these motor neurons based on their corrected activity in a completely blind way. And that's the interesting part. So this is a number of motor neurons recorded during a number of tasks, and then blindly, you don't have any information, you do a latent analysis, and so you look how many latents, meaning how many independent commands are in those motor neurons, and which motor units or motor neuron contribute to each. And now here you see the clusters very well. So they come out naturally. And then when you look at the neural input that each of these clusters receives, then these are the neural input that exactly corresponds to the different tasks. So that means that blindly you can reconstruct the neural control of that arm by having projected the nerve into a muscle and decoding back the neural control. And of course you can then project these commands into an high-level robotics that in principle can control single fingers. Okay? I finish in 30 seconds, but then you will of course ask yourself, well, why do we have to do it only with one nerve? Why don't we take all the nerves innervating the arm and put them in a single muscle and use that muscle as a bioconnector in the same way? It doesn't matter if you have one polyfunctional nerve or 3, 4 nerves. And that's what we would like to go. We are not there yet. Well, by the way, in terms of one nerve, we also have shown the online control earlier in the year. But the interesting thing, in my opinion, will be, we are not at the preclinical study, we are just at the preclinical study, is moving more nerves in the same muscle. So this is an animal study, as you can see, in which 2 nerves have been directed in the same muscle. And again, this muscle has been interfaced with microelectrode arrays. And again, you can distinguish in this case neurons belonging to different nerves in this case. And within that those nerves, neurons belong to different functions. So our idea is that you can bring all the nerve structure of the missing limb, put it in a muscle, use that as a bioconnector, and then fully mathematically infer the full neural control of the missing limb. So in principle, that is possible. In principle, you can decode any kind of movement of the missing limb. In principle. In practice, this is very complex, as you can imagine. All right, thank you very much. Thank you very much for that.
Due to time and setup limitation, we will show them separately and also using some pre-recording data. So now we can start. We have our subject, Greg, that is already prepared. We put on the format 164 electrode grid, and we are using 164 plus device. And now Roberto will show us the interface.
So, let's say, technology as usual. Okay, back. Okay, so the idea for today is to show you a few modules of our software. Let's say that they are made for our particular workflow. It's general enough. So in particular, we will start from the signal recording. So we made a custom acquisition module just because we need, for example, to acquire signal in a particular way. We need to have a feedback for the subject that is, for example, two-dimensional, and so just to have something that is useful for us, we make our own signal acquisition module. So the general idea of the software would be that anyone can develop its own module. So in our case, we have this signal recording module, then we will have the composition, we will have the cleaning of motor units, we will have then the analysis of motor units, and you can enter the workflow anywhere you want, because we try to make it so you can use some very common formats for your data, so you don't need to record with this part. You can record with whatever, like a key format or any other or standardized formats, and then you can enter the workflow wherever you want. So the idea here is that in this case we will start from selecting our device, in this example, we will use one 64. We could use a couple. We use the 64 channel grid, and in particular, here it's this device we're using, but we are planning on releasing, let's say, a way to define your own class to acquire data from your own custom device in a way that you don't need to know how the entire software works, but you can just know the inputs and the outputs. So, for example, you need to know what the device, how to connect to the device, you need to define that, and what's the output of the device. Once you define that, you can use the rest of the software. So, we have our 64, we connect to the 64. Of course, as usual in these conditions, nothing goes as planned. And in particular, since the 64s are wireless devices, they're very subjected to, generally not, but when you have 40 phones and a few Wi-Fi's around here, of course the connection is an issue. In particular, in this case, for example, you can see that every now and then the acquisition kind of staggers because the Wi-Fi signal is not clean. So usually in the lab we make sure that no phones are on and there are no other signals around to make sure that we don't lose any packages. So this is our signal that we are acquiring, and now Greg is contracting just to show EMG. You can see every now and then we will lose some packages. In normal conditions, this shouldn't happen. And then we have the auxiliary channels. For example, if we have force, of course, it becomes a bit noisier. But we have force in the second auxiliary channel. Okay, once we've done that, we have a step to verify that the signal we're acquiring, in this case, not a very good signal, because the setup is not a lab setup, of course. So we do generally one thing, which is to evaluate the root mean square error to see if the baseline is clean, and in this case, just to do a quick check if there are a lot of, for example, dead channels or channels that do not do what expected. We also try to do a contraction and see if the signal-to-noise ratio is good enough. So we try to stay to the rest phase, and we measure that. We try a contraction, and then we analyze whatever we got. Here that the results will be quite bad. Just because one, we lost a lot of packets we were collecting, and then the signal is not very good. And so, in general, let's say this is not the signal we would use in say, an official recording. Here is the grid we have, and for each channel it's telling us that the root mean square and the signal-to-noise ratio is not very good, so it is not usable. So, in general, once we see that some channel is not good, I don't know if you want to.
Yeah, so basically if we see that we have a number of channels that are not up to our standard, we would then look to see where the issues may be coming from. So these could be, if you see something like, depending on the country you're from, 50 or 60 hertz noise, you could investigate to see if something may be touching a piece of metal or a piece of other device. You could also then investigate to see if there's anything ambient that may be causing this noise. And then the last thing we would look at is to see if our electrode placement is correct. So you could massage the grid very gently to see if it could be a contact issue, or you could then either replace the grid if you felt that it wasn't causing the effect you needed of cleaning up your signal. But generally we don't move forward. And also, yes, you can re-wet your reference to make sure it's wet enough to have a good contact before we move forward. But for the sake of time, we will have to move forward.
So the idea here is that, in particular, if you see, for example, usually you might see if a group of electrodes that are close together are not very good, it might mean, of course, the general cause is that that part is damaged or it's not properly connected to the skin, and so you can redo that part. So, assuming that this part is okay in the lab setup, we can do our own let's say, feedback setup, so we decide what kind of feedback the user should follow. And in this case, we check which auxiliary channel we are using for force, which is the second auxiliary channel of the device. Then we do a rest, you say rest like that, and we have a couple of seconds to measure the baseline to see if it is measuring, if it's not zero, then we can contract it. Vediamo così. And let's see, that's enough. So you can save your MOC that you measured if you want, and automatically here it picks up the top force that you measured, or if you want you can take a look at whatever you have, and maybe there might be some artifact somewhere. You can decide, okay, I'm not using the top, but if there's an artifact, I use something slightly lower. But generally, this is just a check. You can redo the MVC, but you can see there's something weird going on. So after that, you set up the shape that you want. In this case, we do a trapezoid. So we decide that the top, the plateau will be, for example, a 10% MVC, something. We do 5 seconds, and we move up by 3% each, or 2% each second, and a plateau of 10 seconds, so 5 seconds. And in this case, it will be the subject will get something like this, and we can try, but it will be a slight issue to measure correctly. So start. If you see like this, that there is a you can put it later than here. It kind of knows how to do that. So once you've done that, you can record it. If you can see, for example, in the beginning that you restart again. In this case, it's close to zero, but if you notice that it's not zero, you can redo the baseline and restart from the beginning, recalculate the baseline and restart. And so, even in this part, one thing is that it will be recurrent for all the things we show. We do something that works for our lab, but we want to make it so it's kind of easier to introduce things that other can do. For example, other feedback types, two-dimensional types, like is the one that we use. So we will make it so to be other modules or plugins that you can attach to introduce other feedback types or other devices, or later on you can, for example, introduce your own way of doing decomposition, way of doing analysis. It should be straightforward to introduce something new using the structure. Like you want to do acquisition bottom analysis, you can use the analysis that you want and attach to our software. So that's the general idea. We then move to the next steps. So a bit of pre-processing, then decomposition, and clean water units and analysis. So
could you please do it in the same, because you are recording from the antagonist and you are doing flexion, correct?
We're just, we just put one grid on for the sake of speed, but yeah, we could do it from the other side, and then have the antagonist in, yeah, for sure.
Yeah, here we don't have any dynamometer, any reasonable setup to acquire data, and also the noise is terrible. So for today we have a backup file that we will decompose and then show you. Yeah, that's, I mean, The goal of today is just to show you a pipeline, a framework that everybody can soon use. But of course, we are far from an ideal condition. So, if you can see my screen, we have the 4 modules that we developed at the moment. Before, we have recorded the signals, and now we can go to the decomposition of these signals. So far, recording signals, then doing decomposition, then analysis would have required to migrate across many different softwares and tools. And now with this platform, we try to allow essentially anybody to perform everything in the same place. So in this example, we open a file that we have already collected, that is a good signal, that's coming actually from the vastus lateralis. You can see here that we have 64 channels and about 34 seconds of duration of the conduction. So usually when you load a file, you may want to resize your file. So in this case, you may want to remove excessive duration of the baseline, or you might have a pre-activation or pre-contractions. And so we can select the area. Okay, now just an example, we don't even necessarily need to remove it, but we can resize this file to only decompose the part that we are interested in. And then the next part that is always needed, or at least it should be always performed, is to look at the EMG signals, to look at the channels, and understand if there is some noise. I can leave the word to Greg, that maybe can...
So generally what we'll do in this is we'll go through channel by channel, we'll look to see if there's any noisy or any dead channels and remove those from the signal. Basically just to save time, because you wouldn't find anything in terms of electrical activity anyway. So you can see here, if I can stand up, what you can see here is we have this nice quiet bass line at the start and the finish. So generally we try to have 1 or 2 seconds of nice and quiet at the beginning and the end. And this allows us then to identify something like this, where you can see noise throughout. So something like this channel here, we would simply remove from any decomposition, and this would save time because there's really nothing in the signal anyway. And we can see here that if we continue on throughout, we can continuously see these nice quiet bass lines at the start and then nice quiet bass lines at the end as we go through. So in this specific example here of a 64, we've only lost 1 channel, which is quite good.
Okay, and then once we have performed this quick pre-processing, then we can start the decomposition. Now, the decomposition that we have implemented is the algorithm proposed by Francesco Negro in 2016, with a bit of, let's say, improvements that the algorithm experienced over the years. And we can do a lot of adjustments to the decomposition parameters, but probably the 2 most important that everybody knows are the number of iterations, because at every iteration we try to detect some motor units, so the more iterations we do, the more chances we have to find motor units. And then the second one is the silver score, which is the accuracy of detection of the motor units. We usually aim for a high silhouette above 0.9, which means that the decomposition worked pretty well, but also that it facilitates our life when we go to the cleaning. We can lower a bit this value, but then we will have much more work to do manually during the cleaning phase. So for today, we will just run 10 iterations of the decomposition, just as an example, and I think Roberto can now explain us a bit what happens during the decomposition.
In this case, you can see here that the algorithm is starting to find some motor units. You can see at the bottom the spike trains. Here at the top left, you can see the activity index, which is basically the square of the EMG signal. So we can detect as a starting point where there is more activity, and we use that to start as a guess to identify the initial guess for motor units. And you can see that every now and then, once motor units are found, the corresponding indexes for the samples of that motor unit are removed in a way that we do not find again the same motor unit, and at a certain point the algorithm will converge because there is now it's finished its iterations, but it might finish, for example, the samples available from the activity index because they found a lot of motor units, either good or bad, and those motor units finished the samples available. So in this case, we can see that we found a good number of motor units, not all very good. Some of them we will have to clean later or even remove if they're not good enough. We will see the examples. And once we got this, we can then move to the next stage, which is the cleaning of the actual motor units that we discovered.
Okay, and now a nice feature about having all integrated in a single software, in a single platform, is that of course we can save this file, and it is actually suggested. But if you want, especially if you're doing some testing, you can directly take this file and transfer it to the next module. So in this case, we want to go to the cleaning part. And in order to do the cleaning, we have an interface that has been specifically created for this, which is probably different from what you have seen until now from other, let's say, cleaning platforms, because there are no buttons essentially. And all this cleaning interface has been designed to work with shortcuts, so with mouse and keyboard. And that has been done in order to be extremely fast and efficient during the cleaning procedure. And all the platform has been designed to be as fast as possible. Now, I will show you a couple of examples, but I need both hands. So there are, we can, for example, go through different units. If we find some units like this one that we can understand it has not been properly detected, or at least not in a way that we could use for any analysis, we can obviously delete it. Or in other cases, if we see that there have been errors in the detection of the firings, I hope you can see them, we can manually adjust the results. So in this case, we can add the missing firings, and you can see that the discharge pattern is changing. And we can do it where we consider it necessary. When we are satisfied about our selections, we can recalculate the separation vector, we can calculate the decomposition filter, and then advance through all the motor units until we are happy. A very important thing that we need to observe, obviously, is the silhouette score that, together with the visual examination of the separation between the noise and the signal cluster, tells us about how good this motor unit is and how much reliable it is. Now, we need to go fast, so we don't have time to show more examples. But we also have the final module that you may know better because it's containing what already is available inside OpenHDMG. That is the one that allows us to do the analysis of what we have decomposed and cleaned at this point. Here you can see the raster plot with the discharge times of the different motor units. In this case, we have 18. We can do some sort of pre-processing that can include filtering signal or simply rearranging the motor units based on their recruitment order. And then we can do very easily basic analysis, like for example calculating the discharge rate. In this case, we select, we tell the algorithm what the steady state is, and we immediately get all the results in this table. We can save it, we can export it, and so on. But we can also do more advanced analysis, like for example tracking, conduction velocity estimation, and so on. Just to give you an example, I can select the sorting order that I'm using for my grid, and you can obviously specify whatever sorting order you prefer that you use for your own grids, and then we can run the algorithm for estimating conduction velocity. Okay, we don't have time to go much more in detail because it's 2:30. I just want to conclude. Thank you. Just want to conclude this presentation first of all by saying thank you to all the people that contributed to the OpenHDMG project, because all what you have seen now is built on top of OpenHDMG, and all the new features that you have seen in this software that are not already in OpenHDMG, will become available open source as well. So thanks a lot to all the collaborators, and if you want to know when this software will be available to the public, when we will start the beta testing, which will likely start in October or anyway very soon, please scan the QR code, so you will be included in the mailing list, and we will inform you about the advances of the project. Thanks a lot, and I think we are... I think we can have questions if you have time, if any.
If there are no questions, I would like to hear you from you. Okay.
Thank you. What's the minimum number of channels required for this kind of analysis?
In general, for any decomposition task, I would say more channels we have and better it is, but likely starting from 32 on, so 64 is usually the standard, but in some muscles, if the signal is good, 32 channels work as well. So yes.
Thank you for the presentation. Do you usually implement any, say, like band pass filters or anything? For example, like 20 hertz and below, I think can be for just like impedance, and like smaller, I guess, like electro drift, for example, and then 400 and above is usually noise, for example.
Yeah, so now we didn't show this part, but obviously you can either decide manually to filter the signal with a bandpass filtering, for example, and you can decide your own range, which is usually 2500 or 2400 Hz. And for the decomposition in particular, we also usually use a notch filter that allows you to improve the power line interference. I mean, it's not strictly necessary, but it's something you can do, and you can do from the software itself.
Similar as Python, so it's like middle ground between these two languages, so it's the best way to show, I feel that it's the best way to show them further. So, as you saw during these 2 days, EMG recordings have evolved a lot over the past decades. We can now identify in real time the activity of motor units and display it to participants, but it's not a new thing. In the 60s, Basmajian was able to give feedback to patients using these fine wire electrodes implanted in one of the hand muscles, and use an oscilloscope and audio amplifier to give feedback about the firing rates of these motor units. And it showed that the patient was able to modulate this activity in real time. So it was like the first step toward what we are doing today, which is using the activity of motor units to interface in real time with computers and machines. So of course, with decades of research, we moved from intramuscular EMG and fine wires to grids of electrodes that just stick over the skin. And in this example, you have a grid that is, I think, grid from OTB. That's a square grid of 64 electrodes sticked over the biceps. And the experimenter used in real time a decomposition algorithm to separate the activity of 3 units from the biceps. And what you can see here is that if you look at the video, you can see that the participant is doing elbow flexion and pronation, supination, which are like the 2 actions that the biceps can drive. And by doing so, the participant is able to separate the activity of these 3 units. So this is what it does here on the right. And if he's able to selectively activate these units in 3 separated commands, then it means that this participant can drive 3 separate tasks for its prosthetic. So this was enabled by the concurrent development of new recording techniques and cuts. So in terms of recording techniques and electrodes, so you saw new electrodes developed by Tyler's lab. So we have 2, let's say, different families of high-density NG electrodes. On the left, you can see a new type of grids that have more electrodes that are denser with small inter-electrode distance. And we found in this paper that basically if you increase the number of electrodes over a single muscle and that the grid of electrodes cover the entire muscle, you can increase the yield of the decomposition. And with these techniques, we found in single muscles up to 90-95 motor units, which was a jump compared to what we were able to do before. If you want to be more specific and specifically target compartments of muscle or small regions of muscle or even like deeper muscle, then you can also use this, let's say, high-density intramuscular arrays of electrodes. And you have different groups developing these electrodes, Dario, but you have a group also in the US, Samson's group. And basically, here you have thin films electrodes. So thin films are like plastic films that you implant and push inside the muscle with a needle. And along this array, you have up to 40 electrodes. And with this, you can span a much larger region than with fine wires and identify much more motor units. So the nice thing with intramuscular arrays is also that it's very specific. So when you look at the recordings, you can even see the action potential by just like single action potential, and you could even separate the action potential by hand. So of course now you have automatic algorithms to separate these intramuscular action potentials, and this is an example of an open source software that you can find online on this GitHub, and this GUI enable you to separate the activity of intramuscular action potentials from multiple units. And the algorithm they use is a spike sorting algorithm, so it means that they detect the shape of multiple motor units across multiple electrodes, and then they sort the shapes to sort and separate the different motor units. The issue when you move to surface ENG is that you have the propagation of the intramuscular action potentials toward the skin, and this travel acts as a low-pass filters. It means that it smooths the shape of the action potentials. And 2 units that look different inside the muscle, like those two, can look the same at the surface of the skin. So that's why with surface ENG, the spike sorting algorithms, like the one I just showed you, will fail to discriminate these 2 units and multiple units in real experiments. So the solution for that is to use grids of electrodes where you can identify the action potential of single motor units across multiple electrodes, and use blind source separation, that are algorithms that will separate the source of the signal, which are the motor units, by identifying their single spatial distribution across the electrodes. And it does it in a blind way, so it means that you don't have to do anything, it's just like an iterative algorithm I will just show you. And one of the most used algorithms today, I think it's the one used in the software developed by OTB, is the algorithm developed by Francesco Negro. And this algorithm was also the algorithm used yesterday in OpenHDENG, the software developed by Francesco's lab. So you have here multiple GitHub with implementation of this algorithm. You have also, so I don't update it, but you have also OpenHDENG that proposed an implementation of this algorithm with a GUI. Or you can also look at this GUI I developed, which is coded in MATLAB, so you need to MATLAB for that. And you can have at the same time the decomposition panel to decompose the signals, and the edition panel to visualize the results and manually edit the signals. I will come back to this later. Okay, so now I will just show you how it works, step by step, and we'll see together the code behind this algorithm. So first, as all algorithms, you need to import the data, and so you need to load the raw ENG file, check the configuration depending on the grid you're using, or if it's intramuscular or surface ENG, because for this you need to change some features, for example, and then segment the session if you've done different contractions. So these algorithms have been optimized for isometric contractions. So most of the time you need to display to the participants force feedback, as you saw yesterday. And then the participants has to reach a plateau of force where the signal is very stable. And this is where this algorithm excels. And during stable period of force, the algorithm will identify stable units. The second part is pre-processing, so you have three separate actions. The first one is filtering, one-pass filtering, some notch filtering to remove light interferences. ENG signal extension, which is a way to computationally increase the number of channels, and whitening, which is a part where you remove all the correlated part of the signals across channels to only keep the part that is unique to each channel. So I will show you this now in the code. Okay. Okay, so as I said, I wrote a Jupyter notebook where you have all the guidelines to install the necessary packages and languages to run it. And I don't know if you're familiar with Jupyter Notebook, but it's a nice way to run code step by step and see the output after each step. So first you just need to install the package if you don't have them, and to load some functions. So I just need one Python function to load the data. Something I didn't discuss with you is the format of the data. So basically we need in the data, and this is what you have when you import a file from OTB, you need to have at the same time the signals from all the channels, but also the configuration of the array. So depending on the grid you use, we need the map to know exactly where were the signals over the electrodes. So there is also an open source format that is more and more used in the field. It's called BIDS, B-I-D-S. It was developed originally for EEG, where you also need to know the map of the electrodes over the scalp. And it was adapted for identity ENG, and it's becoming more and more common, and I think most of the tools will soon use BIDS formats. So just to show you basically what you get with for one recording in BIDS format, so you have on the top corner these 5 files. And if I go if I go to this file, basically you have all the information from my recording. So in this recording, I have 4 grids of a single muscle, and here I don't know if I can zoom in. No. So I have the name of the channels, the type of the signals, the sample frequency, and the most important, the grids we use. And because we know the model, then the algorithm is able to extract the map and reorganize the data automatically. Okay, so I will just load the data from the file. And then here, you can see basically how the code is organized. So yeah, so it's difficult to read it here, but basically if you download it from the GitHub, you have on the top a description of each function with the arguments of the function and the output of the functions. Then it's like in MATLAB, for example, you declare, you have your function here with the name of the function and the input variable you need to run the function. And at the end of this function, you have the return, where you have what you output from the function. So here in this function, to read the image signal, I will just import my files, and it will output a dictionary where I have the signals and the information about the grids. Okay, so you can see here the EMG per grid, the number of grids, the auxiliary data, which are here the force and the path we display to participants to track a pattern of force, and the channel mask if I need to remove some channels that were noisy. Okay, so if I plot the data, so here first you can see the type of contraction. It was a trapezoidal contraction, and so the blue is the target and the red is the performed path by the participants. And here you'll see the EMG signals from 5 channels. If I zoom in, you can see here that, so it was recorded in monopolar mode, and you can see here that across channels you have very similar waveforms. And this is because the grids are dense, the electrodes are very close from each other, so it's normal to have similar waveforms in the signal. So that's why then we perform the pre-processing steps, as I said before, filtering and whitening. So here you have all the functions to do that. So you have a notch filter to remove line interferences. You have a bandpass filter to filter the EMG signal, dim-in to center the signals, and then the function to do the whitening. So I will just load the function by running this cell and perform the EMG pre-processing of this entire contraction. So as you can see, Julia is very fast, so it only takes 2 seconds to do all these steps for the entire signal. So now if I plot the signals right after this processing stage, you can see that if I zoom in the same area, the common waveforms have disappeared from the signal. And this is why we do whitening, to only keep what's unique to each channel, to identify the unique spatial signature of the motor units, to extract them from the EMG signal. Okay, so this is like all the pre-processing steps before the actual main part of the decomposition algorithm. So if I jump back to my slides, so I'll just show you how we import data, and I show you the new format called bits. The pre-processing step to go from raw EMG signals to whitened EMG signals. And now the most important step for the ratio separation is the identification of what we call the pulse trains. So the pulse trains is a train of peaks that represent the discharge types of each motor unit, and the algorithm will optimize a filter for each individual motor unit to make this pulse train the sparser. So I will just show you now how it works. So basically, we initialize a set of weights for each individual channels, and we use random weights. Then the algorithm will optimize these weights to skew the distribution of the values of this pulse train toward the left, which means that we want the algorithm to optimize these weights to get most of the values as close as 0, and the very low number of values as close as the maximum. And like this, you'll see here that peaks starts to appear, and these peaks are the very sparse discharge times of the motor units. On the left, you can see what we call a separation vector, which is what we optimize in the algorithm, and we do that for all motor units. And at the end, after a few refining steps, you can see here that we use an algorithm to separate the high peaks from the low peaks, and the high peaks are the spikes, the action potentials, and the low peaks are the noise. And of course, the higher the distance between the high peaks and the low peaks, the easier it is for the algorithm to identify the action potentials. So this is also something that we use to know if what we decomposed was accurate. After running this for, let's say, the first motor unit, we can do what we call peel-off, which is removing the action potential of the single motor unit from the signal to run the following iteration on the residual. And like this, it means that you will not identify the same motor unit twice, if that makes sense. So for this, so you can see here on the top the signal, the original signal. On the bottom, you can see the identified discharge times. We identify the action potential waveforms by segmenting the EMG signal at each discharge time. We average it across all the discharge times to quantify this waveform. Then we recreate a train of action potential for the single motor unit, and we subtract it from the signal. And like this, we get this residual, and you can run the next iteration on this residual to identify a new motor unit. And that's why you will converge to always new motor units. Yeah.
How many iterations?
Depends.
So you suggest?
It depends. So the higher the number of iterations, the higher your chance to identify more motor units. But sometimes, after a few iterations, your algorithm will not find any new motor units because the signal is noisy or there is not much identifiable motor units in your signal. So it means that, for example, if you use always 1000 iterations, it will be too demanding for your computer and not always useful. So I would say that if you have beautiful recordings and you're sure that you can identify a lot of motor units, then you should go up to 200, 250 iterations. If you see that after a few iterations you cannot find any accurate motor units, and I will tell you how we define what's accurate or not, then it doesn't matter if you have 1000 or 50 iterations. So this is just to show you what we identify without the peel-off and with the peel-off. So without subtracting or with subtracting the identified motor units. On the left, you have intramuscular EMG decomposition. On the right, surface EMG decomposition, and the red trains of action potentials, or the new identified motor units thanks to the peel-off. So you can see that using peel-off adds a lot of motor units for intramuscular EMG and a decent number of motor units even for surface EMG. Okay, so let's go back to the algorithm. Okay, so here you have all the functions you need to run the decomposition. So the fixed point algorithm is the part that optimizes the weights. The get spikes is just a function to identify the peaks and separate the high peaks from the low peaks using k-mean. And then you have a second loop that optimizes again the weights. If you want to see the different steps of this algorithm, beside the code, you have a paper from Francesco Negro, the original one, that describes all these steps. And then you have a last function here that is called calc seal, and seal is the way we identify an accurate, we estimate the accuracy of the motor units. And for that, basically what we need is to calculate the distance, as I say, between the high peaks and the low peaks. And by doing so, you can estimate a silhouette value that should be as close as possible from 1. And if this C-weight value is high, then you can be sure that the separation from the high peaks from the low peaks was pretty accurate. So on this example, you have 2 individual extracted pulse trains in 2 iterations, but you can see that on the right, it's much better than on the left. So on the right, the C-weight value will be close to 1, when on the left, it will be closer from 0.9 or 0.8. So this way we can already identify the units that were good in the decomposition. Okay, so I just go back to the code to run it. So I load the functions, and then I will just run 15 iterations. So it should take not that long, I hope. So basically it's iterating 15 times what I just showed you: optimization of the separation vector, separation from the high peaks from the low peaks, and then peel off if the identified motor mix is accurate. Okay, so it's done. 32 seconds for 15 iterations is not bad for the entire contraction, entire signal. And I will just display the units identified at iteration 2, just to show you the output of the algorithm. So this is the pulse train, and the red dots are the identified peaks. So you can see here that the distance was pretty high on the peaks, between the peaks and the noise. So it was quite easy for the algorithms to identify and separate each peaks. So you can also see that here, for example, you have some missing spikes. And this is because we use only 2 classes with scaling clustering to separate the high peaks from the low peaks. And because the height of the peaks is not always high, sometimes you miss some peaks. And that's why you need what we call manual editing visualization. So this is a step where you need to go back to this pulse train to visualize them and to select the missed spikes. So basically what this step does, so you need to, so you have first the automatic decomposition, and then you need to remove and add spikes that were either missed or wrongly associated with the spike class. And for that, to identify them, you need first physiological knowledge to know what you should expect from the frame rate of your units during, for example, an isometric contraction, and patience, because it's a very long process. So here you can see after one step of manual editing, so I only decomposed a segment of a contraction. So I identified all the wrong spikes by looking at the frame rate, and all these peaks here in the frame rate should not be are not physiological during a stable isometric contraction. So we should expect something that is pretty stable and variable due to synesthetic noise, but that in that case stay around 20 spikes per second. Of course, sometimes you can have high frame rate due to doublet. For example, we discussed this yesterday. So one way to know if you have a doublet and not a wrongly selected spike is to look at the duration of the interspike interval after the doublet, and you should have a longer interspike interval after the doublet than expected. Okay, so once you corrected the automatic selection of peaks, you re-evaluate, you re-update the weight, the separation vector or the filter, to identify the pulse train over the entire contraction. So this is what you have here, and the last part is to clean this to have what you should expect from the behavior of this motor unit during the contraction. Okay. So this is the example of what you get after the automatic decomposition. And I can show you this. This is sorry. Okay, so this is the action potentials, average action potentials identified over all the channels for this single motor unit. So you can clearly see the waveform and the differences between electrodes due to the distance between each electrode and the position of the motor unit within the muscle. Okay. So now just a few things about new developments for this algorithm. So I just showed you, let's say, the most common implementation of decomposition used today in the field. So you have some developments, and mostly developments from Dario's lab. Now most of these developments are open source, so this means that you can find the code online on GitHub and use it yourself. So first you have here what's called the swarm contrast kit decomposition. And what Agnese developed basically is a new way to optimize the weights for the motor unit. So instead of running the optimization of the weights one time, she, a parallel processing way, optimized multiple separation vectors for the same motor units and select in all these iterations the best one. And in that way, she showed that she can identify more motor units than what you could identify with a classic plateau separation. So go to her GitHub and you will find the implementation right there. A second thing is what we call adaptive decomposition. So I showed you an example with isometric contraction where you have a trapezoidal contraction and a plateau where the classic algorithm performs well. As soon as you perform some movements, this will be more challenging for the algorithm because the position of the motor unit related to the crease will change. It means that the unique spatial signature of the unit that we use to identify it will also change. So it means that we need to adapt and take into consideration these changes to keep identifying the same motor units across the entire contraction. And for that, what Irene developed is an iterative process to optimize at the same time, to update at the same time the whitening matrix, the separation vector, and the threshold we use to separate the spikes from the noise. And I just show you what it does. So this is a simulation, but it performs well on experimental data. So this is what you would have without any adaptive decomposition during the case contraction. So basically she was performing a wrist flexion, and she was here between each plateau changing the angle of the wrist. So the muscle was moving. And that's why you lose progressively the motor units. And if you use the adaptive decomposition with the iterative updates of this part of the algorithm, you can keep identifying the unit. So again, in the code, I have a very simple implementation. It's not the exact implementation of Irene's algorithm, but it's a simple one where I update the separation vectors and the threshold to identify the spikes. So you have the function here, and I will just run it on the code to show you what it does. So this is quite fast. You can also use it in real time. But basically here you can see the blue and the red. These are the changes between windows, separated windows of EMG, to automatically adapt the parameters to the change observing the signal. And even if it's isometric, I showed you before that some peaks were lower than others, and you can see that with this adaptive approach, you can have a better adaptation of the thresholds to follow the change in the page, for example, to keep identifying the peak even if you have some differences. And it also works if you have like slow contractions or ramp up or ramp down. It enables you to improve the decomposition during these conditions. Okay, the last thing I want to show you is what we try to push again with people in Dario's lab. It's a benchmark for decomposition algorithms. So more and more people are using this algorithm or developing new versions of these algorithms to identify more motor units. And I think there is also like more and more events used to perform like competitions to have the best decomposition algorithm between labs. And we need a proper benchmark to compare these different algorithms and see which one performs the best. So we submitted an abstract. We submitted a paper to NeuroX this year, which was just accepted. And basically, we propose a way to benchmark the algorithms by giving first access to data sets in the BIS format, tools with the current implementation of decomposition algorithms, such as Black-2 separation, the swarm, contrastive decomp I showed you. And so you can find all these tools in the benchmark. You can find also a simulator to simulate EMG signals to compare the performance of your own algorithms to this current implementation of source separation algorithm and try to develop your own approach, hopefully increasing the ability of these algorithms to identify more motor units. And with that, I thank you for your attention. I don't know if you have any questions. All these people have contributed, of course, to the development of these different tools. So thank you. Just let me know if you have questions, you can come.
Yeah. How you can recognize the same motor unit in different lengths and how much isometric contraction you need?
So can I track the same motor units?
Yeah, when you move from one position to the other, you don't have the same signal.
Yeah, it's the same signal. We have a continuous signal, and we just segment it in the short windows. And so we adapt the filtering and the spike thresholds in all, each consecutive window. So we can continuously follow the motor units and identify the subtle changes in electrical control shapes, for example, by tracking it. It has been validated with simulations, and of course it's difficult to have like ground truth in humans, but we have simultaneous recordings between intramuscular surface.
Thanks for the presentation. Do you see any problems with a pipeline including multiple decomposition algorithms?
So what do you mean by multiple decomposition algorithm?
For example, you showed different ways to decompose.
Yeah.
So if you decompose using two different algorithms and then merge and find the common and not common units, do you think that could be a great idea?
Yeah, that works. You just need to be sure that you're not overkilling the problem here by identifying the same motor units with both algorithms. But if you, for example, in the swarm, they optimize multiple features for the same motor unit and then select the best one. You could do that with multiple algorithms if you want to. You just need to be sure at the end that you don't have any duplicates, like looking at the discharge tags, to be sure that you don't have the same discharge tags for the two motor units.
I wanted to ask, so for example, like in the forearm, it's like a very sort of like complex alignment of muscles, right? And sometimes like if you put EMG in your wrong spot, it could end up like sitting on the bone, let's say. What, I guess, pre-processing methods would help with decomposing VM using the forearm? Like, is there anything specific you can do? And like, what other muscles are hard to decompose than others?
Yeah, thanks for the question. I think it's a very important question. So decomposition works well, but it works better in some muscles and some people. So for example, we know, and Greg has a project on this, that in general, on average, we don't find more motor needs in male than females. And this may be due to the tissues, even if we are pretty sure that it's not the main part of the problem. It may be due also to the properties of the motor needs themselves. So that's the same issue with muscles. We have muscles with different number of motor units, different size of territories, which mean different amplitude of signals on the skin, and different geometries with some pinnate muscle, fusiform muscles. So we need to unlock some things to optimize the way we identify motor needs in each of these muscles or people. But right now there is no options in the algorithm to optimize the decomposition for one muscle or another one. We just know that it works better in some. This may be mitigated by intramuscular EMG because you're closer from the source and it's less sensitive to the propagation of the signals through the tissues, through the skin. So yeah, maybe a way to do it. Another issue is the forearm muscle, because it was the question. They're so small that you don't really know if the unit you identified is from the muscle that is right below, under the electrode. So right now the electrodes are so big that you could have motor needs from multiple muscles identified in the same electrode.
We are late, sorry. I suggest to move to the other room, otherwise we do not make lunch.
We have to leave at 1? Okay, probably start the last round. So, for us it's the third time, probably it's the first. So Laura is presenting how to combine surface EMG signal and ultrasound for neuromuscular control studies and human interfaces. The workshop was expecting to have another colleague with Laura with the ultrasound part, but the flight was cancelled, so it's still in London, and so we will try to show you, Laura will try to show you the concept, not the full system working, but just an idea, and it's pretty clear, I would honestly say.
Thank you very much. Welcome to the workshop. I'm also sorry again about this, but I made some last minute slides, and we should be able to go through also the full experimental pipeline as we planned, even if you are not going to see the ultrasound or the prosthesis moving, but still something. So I'm a postdoctoral researcher in the biomechanics and rehabilitation technology lab at Imperial College. I mostly focus on intramuscular EMG, so it's also a bit different. But today we look at a different modality of interfacing, and we made this choice because we know that many of the people in the audience are mostly familiar with EMG. So today we look at how we can combine EMGs and ultrasound. So I won't repeat it again because you know it very well. There is just one thing that I want to highlight. That is that when the action potentials get to the fibers, they trigger the depolarization of the fibrous membrane. But also they start this excitation-contraction dynamics. And what this is telling us is that the force generation process is not only an electrical process, it's also chemical and it's also mechanical. So if we could have a modality that is not only EMGs but also ultrasound that is looking at deformation, how the mechanical structure is changing over time, maybe we can get a denser and richer information about the motor intent and use this for interfacing. So just a very basic introduction to ultrasound, in case you are not familiar with. So ultrasound is just based on the propagation of mechanical waves. So here you have a transducer here that is made of a piezoelectric crystal that will convert electrical voltage into mechanical vibration. And so this wave will travel in medium, so also through our body, our muscles. And when it goes through the tissues, so from medium 1, for example, and medium 2, there are a series of processes that happen. The first one is deflection, the second one is transmission, and then scattering as well. So if we consider most of the medical ultrasound, usually is recording the deflection back. And this is because you have the same transducer that is used to send the pulse, I will explain later, and then record also the signals that are reflected back. So while EMG is a biological signal, ultrasound is not, is a bit different. So with the ultrasound, we need to send a pulse and then record some properties, so structural, for example, and also functional of the muscle. So it's in a sense very different from EMG. So there are two phases for recording ultrasound. The first one is transmitting an impulse, and the second phase is receiving. So here we transmit, and we send a very short pulse that happens in the scale of the microseconds. And this is done by applying to the same piezoelectric crystal a small voltage. This pulse has different properties that can be adapted and depending on your application, and this will of course impact, for example, the resolution, the sensitivity, the amplitude of the signals that you get back. So after we send the pulse, we need them to get the signal, so it's the receiving phase. And basically what we need to do is to listen to these reflection waves. So you get this signal over time, and because we know the speed of sound, we can then remap the time that it takes for these signals to be received back to depth. So the information that in practice we get is depth. So we know, if I go to this slide, for example, so this is using our classic portable ultrasound probe. If we focus first on this image, on this video on the right, so the probe was put transversal to the muscle, so you see the cross section. So you have a depth information, and you see that when you contract, the muscle is going to deform, and so you have both structural and functional information about the movement that you are performing. If we put the probe parallel to the muscle fibers, instead we can see exactly how these are shortening and lengthening over time. So effectively what we get is information that is functional, so it's about the type of tasks that you are performing. So if we just consider this example that is quite practical for prosthetic applications, for example, so typically you want, for example, to map wrist extension, you can see that the state, so the information that we get when the wrist is relaxed and when it's extended is completely different. Here you see these are connective structures, this is the muscle, this is the bone, and you see that this changes over time as you perform tasks. So in the lab, specifically this PhD student Bruno has been developing over time portable ultrasound devices that are wearable, so that we can wear like easily as EMG bands for interfacing. So he's not here today to present, but I just invite you to check the paper from Scalmato et al. So this ultrasound-based modality was used for prosthesis control, and you can see the device is this one in white. It can be very easily put on top of the muscle. There are multiple probes, so you get multiple signals over time. So in this case, it was tested with people with limb loss, and it was demonstrated that it can get to up to 4 days of freedom of control. So this is a classic clinical test that is done, is a cloth pin, so the task is to take those pins and move them from the low bar to the vertical one, and this involves usually movement of the wrists, such as pronation, supination, and of course opening and closing. So it's quite challenging for EMGs, and this is because pronators are big muscles. So if you have something that is sitting on top, it's harder to get that information. So this is one video, and then we also have this other clinical test that is called box and block. So you move those blocks from one side to the other one. So what we wanted to see today is to try to combine the two modalities. So ideally we would like to place some high-density EMG grids and also be able to sample the, let's say, functional activity of the muscle in the same place. And this could be done with these grids that have been produced by the Shenzhen Institute of Advanced Technology together with OT. So the material of these grids, that is very thin, allows you to do a dual recording. So what we intended to do was to basically, so this is an MRI, we wanted to place the grid on top of extensor muscles and also add some channels here that are on top of the FTP, because we know that for EMG is going to be challenging to get the activity of the pronator, that is much deeper, but we wanted to see if maybe with ultrasound we could get that. So this was experimental setup. So we had this grid, and then we had these two bracelets of ultrasound probes. So each of them is a single transducer, and we can move these and we can align them to be on top of these contact points. So we, of course, check the signal before and after putting these ultrasound probes, and it's not affecting at all the quality of the signal, so it's not applying any sort of deformation or other tool. So what we would have done is that we added this interface that allows you to synchronize the two modalities and so get EMGs and ultrasound at the same time. We would train pronation and supination and open and close. And we would train a very simple regression just on these two type of tasks without training combination of movement. And then we would have shown in real time the output of just having the ultrasound, just having the EMGs, and combining both features into one single algorithm. We cannot do this today, but there are some take-home messages that I just want to say. And before going to that, maybe we just check the signals. So to see they're still there. So now I'm relaxed. It's a bit noisy, but yeah, and these are the 30 signals from the 32 channels. So it's very similar in quality to what you would have with the gel-based grids. So these, as you can see, this is a very thin film, so it can adapt very well to the skin, so it adapts to the forms together with your arm as well, so this is a big advantage. We have also tried to remove it and to apply it multiple times, and as long as you can place this thin film on the skin, the quality given by this contact point is still quite good, so we use the same grid multiple times. So just to go back to this. So there are a few common issues of modalities and there are strengths of each. So for example, as EMGs, like EMGs, ultrasound is also very sensitive to the positioning of the probes and to the contact quality, so that is a common thing, but then ultrasound has this information about that, so it allowed us to capture the activity of the pronator muscle, for example, so this is also an advantage. So typically with prosthesis control, what you do is that you map the EMGs into proportional velocity or proportional position control. So what we saw is that, this is of course very preliminary, but is that ultrasound is very good at trying to map the full range of motion. So if you train supination, for example, you are really able to do proportional positioning control, while with EMG you tend to jump a bit to the extreme. And this is because typically when you train these methods, you do the movement and you reach the joint limit and you tend to push a bit. So this is, for example, a case where combining the two maybe would help improving the control. Another thing is that by combining the two modalities, even if we didn't train on the combination of the degrees of freedom, we were able to span the full combination of the degrees of freedom space. So we trained this movement, but then we were able to do maybe supination and cruising at the same time without having observation about this task. And this is probably because of the position-related information that is given by ultrasound. So these are a bit of the strength of the two, and so the take-home message would be that why not trying to combine both. One other thing is that EMG, you generate the signal and you record it, while ultrasound you have at any point in time the functional, like the information about the structure of muscles in the limb. So it's a different modality, a richer information in a sense. So these are very condensed workshop of what we wanted to show, but yeah, I hope you enjoy, and I just invite you to come here to check the grids, and if you have any questions.
I have a question.
Yes.
So if the aim is to improve, let's say,
so I'm Ernest from King's College London. So if the aim is to improve, I believe following the meaning, to improve prosthetic control, for example, the EMG is a passive device, we listen and then we interpret. For ultrasound, which is an active device, you need to power it for the time, power to transmit. So how do you think you manage those batteries that already are draining for the day?
Yeah, I think that is a really good point, but also this is not yet something that is wearable and that can be easily used for control of prosthesis right now. Of course, there are a series of steps for both modalities to be improved to get to that point. So one thing is, of course, the power supply, as you said, but is also making these probes very small. Those cannot be worn at the moment, and they are not yet high density, so you get a kind of sparse information about the structure and so also the functional properties. So there are many directions for improvement. Yeah.
Other question?
Thank you very much for the presentation. I was just wondering one thing. Since you showed an MRI image before, and you mentioned about the sensitivity of the techniques to the placement of the electrodes, I was wondering if you can get any useful anatomical information using that technique, or if it was just for the sake of presentation.
Yeah, it was mostly for the sake of presentation in this case, but also in that case you can get structural information, so you can maybe understand for your specific application how it's best to position these probes. So yeah, it's something that we have not investigated yet. So ideally we targeted the belly of the muscles, but you could optimize it.
Other question? So if not, thanks. Come here, and so just. Yeah.
Thank you very much.
Thank you very much.